stupid questions because I am stupid, and also to motivate the students to ask you questions. By the way, I find that first picture very disturbing, where you located the black hole. But anyway, let's start. Go ahead, man. Only that you're muted.
So I hope you can now all hear me.
We can hear you, we can see you, everything.
Very good. So so today will be a day of mathematics and a day of Greeks. And so the common theme, as I understand it, of my presentation and that of Kostas will be mathematical physics, let's say. But my talk will be completely classical, whereas I understand his will veer into the quantum regime. So what I really want to discuss is the role of mathematics in general relativity. And so I know many of you are coming from a physics background. So many of you, of course, know very well general relativity. And I hope to sort of give you a perspective on the subject coming from let's say, a mathematician, someone who proves theorems for a living. And what I hope to sort of communicate to you all is that mathematics has from the beginning played particularly in general relativity, a very central role, from even before the sort of formulation of general relativity, and it continues to do so now. So I'll somehow try to describe a little bit this role, and let me warn you that this talk is not meant in any way to be encyclopedic. It's really a personal perspective of somehow the role of mathematics in general relativity, and hopefully people will be motivated to explore some of these themes more and learn about the things that I won't get to talk about, because of course, given the time, I will only be able to say so many things. Okay, so this is the plan. And let me also repeat what Pau said, that please feel free to interrupt, interject, question, or anything like that. There's sort of no there's no rush. There's no time constraints from me, at least. So please feel free. Okay, so let me begin with a summary of how this presentation is structured. So as I said, the sort of role of mathematics in general relativity begins even before general relativity was formulated. So I'm going to call this the prehistory of mathematics in general relativity. And so I'll begin with a discussion of that. This will be actually quite brief, but it will get us into the spirit. And then I'll review sort of the birth of general relativity, particularly Einstein's work from 1915 that bequeathed us the Einstein equations. And then I'm going to look at various mathematical themes in general relativity. So the first sort of theme is maybe the most elementary, but still it very much counts as a mathematical theme. And that's sort of the search for explicit solutions of general relativity, solutions that you can write down in closed form in terms of sines and cosines and somehow the functions that we know and love. And so this will be let's say the first mathematical theme. But in some sense, okay, this is maybe the most explicit, this is the most elementary mathematical theme, and one that, okay, sort of is so familiar to people in physics that I don't think they even think of it as being mathematical, even though it is. So then I'll continue with sort of a description of let me say it as follows: of three eras in the sort of the mathematical study of general relativity, and I find it entertaining to put a Hegelian spin on sort of this periodization. So you can think of the first era as being the thesis, and this is sort of the local PDE analysis of the Einstein equations. And this actually begins in the 30s, but in some sense its heyday was in the 50s with the work of Yvonne Choquet-Bras. So I'm going to talk about that. And then there's what I would call the antithesis. So this is another mathematical approach to general relativity that seemed very, very orthogonal to the sort of PDE approach. And this is looking at general relativity, in some sense, from the point of view of pure geometry. And this was also an extremely influential approach. Again, it started actually early. It started, I would say, in the 30s, but its real heyday was in the 60s. And Roger Penrose is maybe the most famous figure associated with that approach. So this is somehow the approach of global geometry. And finally, again, in this Hegelian sort of language, we could call the synthesis, is in some sense maybe the main current of research today in the mathematics of general relativity. And this is really the combination of PDE analysis, looking at the equations of general relativity as partial differential equations, but at the same time in a very geometric way. So I'll call this global PDE analysis in geometry. So this is really sort of the style, the flavor of mathematics in general relativity currently. And I'll try to give you a taste of sort of some of the themes which are of interest in current research. So I'll try to structure my discussion like that. Although I should emphasize that even though I think of this in this chronology, all of these three last directions, even the search for explicit solutions, they are all ongoing. So even though each of these directions sort of had its heyday, maybe in a particular historical era, they're all sort of fruitful directions that can still be pursued. Okay, so that's the structure that I hope to give to this presentation. So let me begin with the prehistory of mathematics and general relativity. So let's begin with this sort of part 0, and I'm going to be very brief. So recall that the general relativity was formulated in 1915, and we'll get to that very, very soon. But mathematics and general relativity, you can say, starts in 1908 with Minkowski. So remember the chronology where we are. So in 1905, Einstein had formulated special relativity. But Einstein's formulation of special relativity, as you'll remember, was still in the language of lifts and trains and sort of frames of reference and this and that. And it was really Minkowski who had the insight, also based on work of Poincaré, to reformulate Einstein's special relativity as the study of space-time. Okay? So it was really Minkowski who introduced the space-time notion with sort of with the important notion of the light cone. And here this is really this is taken from Minkowski's celebrated lecture from 1908. These things in yellow. So here you see the sort of the light cone that he introduced, and even more importantly, the Minkowski metric. Okay, so the Minkowski metric is this expression here: c squared dt squared minus dx squared minus dy squared minus dz squared, and the the integral of the square root of this expression over a path in space-time, this corresponds to proper time. Okay, so all these are notions that first appeared in Minkowski's reformulation of special relativity. Okay, so it's amusing to say that when Minkowski's work first appeared, I was not actually very impressed by it. In fact, he wrote in one of his letters, I don't have the exact quote in front of me, so I'm paraphrasing, but he wrote that this is exactly what happens when pure mathematicians, take their hands on a physical theory. They make it sort of completely incomprehensible. So this really was sort of the original reception of special relativity. Of course, Einstein changed his mind later on. He had to, because he had to make use of this, as we'll see. But in any case, it is amusing to remember that history. Okay, so this is certainly quintessential, let's say, mathematical contribution, which, as we'll see, was fundamental for general relativity. But there's another mathematical contribution which was fundamental, which is even earlier. Okay, and this is, of course, the invention of Riemannian geometry by Riemann. So this famously, Riemannian geometry was first proposed in Riemann's habilitation lecture in 1854. So here again is a little snippet of the printed version of that lecture. So that lecture, unfortunately, doesn't really contain many formulae. So if you're looking for the sort of an expression, general Riemannian metric, such and such, you're not going to find it in that lecture. It's all texts. So actually, this piece of text is the closest you'll find to a description of what a Riemannian metric is. And here, one thing you'll recognize, even if you don't speak German, and I don't speak German, is you'll recognize this number n times n plus 1 over 2, which corresponds to the number of free free components of a Riemannian metric. Okay? So in any case, this notion of a Riemannian metric, so the natural generalization of the so-called first fundamental form of surfaces. So this natural notion of Riemannian metric, which was sort of proposed by Riemann and then sort of further studied by, particularly by the Italian school, by Ricci and Levi-Civita. Well, this was also a purely mathematical contribution, which, as we shall see, was fundamental for general relativity, and all this was even before general relativity was born. Okay, so this is what I want to just say about the prehistory of mathematics in general relativity. Now let's go to the birth of general relativity. Okay, so birth of general relativity. So in some sense, the birth of general relativity was very simple, at least the first part. So many of you may know that in some sense general relativity was born in let's say 2 papers. So the first was actually a joint paper from 1913 of Einstein and Marcel Grossmann. And in this paper, they introduced the general sort of structure of the theory. And in particular, in this paper, they described this insight that gravity should be described by curved spacetime. And what is curved spacetime? It's exactly the marriage of Riemann's sort of notion of a curved geometry, so Riemannian geometry, but with the signature of Minkowski. Okay, so if you want, in some sense, the notion of curved spacetime is nothing else than applying Riemann's procedure of sort of creating a curved geometry, but not based on Euclidean geometry, based on this as your sort of your standard case. Okay? So this is very familiar to everyone. In fact, this paper they introduced this notation here with the G mean E that we all know and love, but where G mean E is now not a Riemannian metric, but it's a Lorentzian metric. But all the notions of Riemannian geometry, all the notions that Riemann introduced carry over, and those notions in this theory now acquire direct physical meaning. So, for instance, the notion of geodesics in this theory correspond to freely falling observers. Okay, and so this metric is in principle measurable, and it has something to do with gravity on the basis of its freely falling observers. Okay, so if you want, this was the first and the quote easy part of the birth of general relativity, understanding that this sort of mathematical structure of Riemann, of course, with this slight change, which is based on the work of Minkowski, was appropriate for trying to incorporate gravity into the framework of the previous special world. Okay, so in particular, already when he wrote this paper, Einstein had changed his mind, obviously, on Minkowski. This sort of this theory, as being described here, could not be explained in terms of trains and people in elevators and all that. You really had to adopt the space-time notion. Okay? So it really was indeed fundamental. Okay, so this is, if you want, the first part of the birth of general relativity, the easy part. But of course, the theory of gravity is not just a description of how freely falling observers would behave in a given gravitational field. A theory of gravity has to give you an equation for the field. And we all know that, of course, from our Newtonian mechanics, right? The Newtonian gravity is not just the sort of the stipulation of how an object falls in a given gravitational field. It is also a rule that tells us how all the matter in the universe, how it affects the gravitational field. Okay. So what about that? How to find an equation for the sort of geometry of space-time? Well, this was the second part of the birth of general relativity, and this was much more tricky. And this was Einstein alone in 1915, 2 years later. And this is his celebrated paper, the field equations of gravitation. And well, here's some German from that paper. And since I don't understand the German, let me get rid of all that text and just focus on this equation. So this is the celebrated Einstein equations. Okay. So these first appeared in that paper. So now equations have a side, and the left-hand side of this equation is something about the curvature of the space-time. It's a particular trace of the Riemann curvature tensor. So it's an appropriate trace of precisely that, an expression that was first introduced by Riemann, the founder of Riemannian geometry. And on the right-hand side is something called the energy momentum tensor of matter. Okay? And this is exactly the form that they were originally written in Einstein's paper. So, so as many of you know, we like apples when discussing gravity. It's traditional ever since Newton's time. So so often this equation is depicted schematically in this little picture that I have in front of me. So we have the matter, which is represented by this apple. So you should think that this is the thing on the right-hand side, and it's by its presence, it's curving space-time. So here we think of this black curve as being space-time, which is being curved because of the matter. So okay, we all know these depictions. But one thing I want to emphasize, and it's sort of counterintuitive, but will actually be very convenient for this talk. So the Einstein equations turn out to be non-trivial even in vacuum. So even in the case where there's no matter, so there goes the apple, the Einstein equations, which then simplify to the form where the so-called Ricci curvature, so this is again a trace of the Riemann curvature tensor, is equal to 0. So the Einstein equations are non-trivial even in vacuum, even if space-time is everywhere vacuum. I cannot emphasize enough how surprising this is if you're coming from the point of view of the Newtonian theory. So Newtonian gravity is, as we all learned in school probably, is you can think of it as being governed by the Poisson equation. So if you have Newtonian gravity of continuous fields, okay, they have a matter density. We can call this, I don't know, rho, and the gravitational potential is governed by the equation Laplace phi equals 4 pi rho. Okay, so Laplace phi equals 4 pi rho. Now, if rho is everywhere 0, that's what vacuum means. And if phi satisfies the usual boundary conditions at infinity, namely the phi is 0 at infinity, then it's an easy exercise. And okay, anyone who wanted a nice exercise in the theory of partial differential equations, well, there's an exercise for you. If you have a solution to Laplace phi equals 0 everywhere in space, but phi is 0 at infinity, then phi has to be identical. Okay. So in the Newtonian theory, the vacuum is trivial. In general relativity, however, vacuum is non-trivial. And in fact, not only is vacuum non-trivial, but in some sense, every non-trivial thing that happens in the theory already happens in vacuum. So to paraphrase my academic grandfather, Johnny Wheeler, you see, this is related to the nonlinearity of the Einstein equations. So you could say it like this: that space tells space how to curve. Okay. So for the rest of this presentation, actually, when I think about general relativity and when I talk about general relativity, I will always restrict to the vacuum case. And believe me, somehow life would be so much better if there was no matter. Anyway, so there's another aspect of these equations that I want to remark on already now, because it's also fundamental both for sort of the physics of these equations, but also for sort of the mathematical theory of these equations. And that is that these equations are of wave type. Okay? So in particular, you can think that curvature of space-time, okay, propagates in vacuum as a wave. Okay? So when you have curviness in these equations, it propagates as a wave. So there it goes, it's gone. Okay? And of course, these waves have been directly observed on Earth now, and there's no this is something very familiar to this audience. But I claim that this wave-like aspect of the Einstein equations, which was actually misunderstood for many years in the physics community, was actually, in some sense, well understood relatively early in the mathematics community, exactly because it's related to various very important mathematical features of the equations, which I'll get to soon. Okay, so this is really what I wanted to say about the birth of general relativity, and this is sort of the okay. So in the rest of this talk, when I talk about general relativity, I'm really going to be talking about the dynamics of the Einstein vacuum equations. Okay. All right. Are there any questions, by the way, already?
I have just one comment. I like matter. You don't like matter, but I like matter.
Well, you know, sort of. We've been accustomed to living with matter and with its consequences, but I still I stand by what I said. That life would be better with no matter anywhere.
But what about the students? Don't you have any questions for him? Because he has said a couple of non-very trivial things, like space tells space how to bend or how to curve. Is this clear?
So, Professor, general relativity actually starts from Minkowski, and Einstein do his works from that.
Yeah, well, so I mean, okay, there's no, okay, general relativity proper certainly starts from Einstein. I'm not, I'm certainly not trying to to sort of, you know, take that away from Einstein. In fact, in this sense, general relativity is really unique in this sense that it is, if any theory of somehow, if any theory of physics can be primarily attributed to one person's personal achievement, then it really is general relativity. Special relativity, even, which we also associate with Einstein, and Einstein certainly had the, sort of the final very important insight on. Many people were sort of involved in its development. Electrodynamics also, of course, you know, we associated it to Maxwell, but it, you know, in reality, many people somehow contributed. I think in general relativity, the sort of the personal contribution of Einstein is sort of decisive. Of, you know, having the idea that this was the framework that was necessary, something that was not at all clear in, let's say, 1908, that, you know, the correct framework for general relativity is curved space-time. This was certainly not clear. But not only did he have that insight, but he also got the equation. And again, okay, he maybe, you know, it was helpful that Hilbert was sort of, you know, fast on his tail. But in any case, I mean, you know, he both had the concept of the theory and he got, you know, the equation, and sort of, okay, it's a that's the definitive formulation. So somehow, no one's trying to take that away. He's certainly, I mean, he is the founder of general relativity. But of course, the theory was based on previous work, and you know, that previous work was mathematical, and was very, for its time, mathematically sophisticated. So, I mean, it's interesting to think about Riemannian geometry, okay? Because of course, today, Riemannian geometry is a big field in mathematics. Okay, if you go to any mathematics department in the world, there will be but actually, at the time of Einstein, Riemannian geometry was a very obscure area. In fact, essentially the only people working in Riemannian geometry at the time, it wasn't even called Riemannian geometry, it was maybe called the absolute tensor calculus. The only people working on that field were Levi-Civita and Ricci. Essentially, though that was the field somehow. So it was a very new and not so well known, at that time, very modern, new direction of mathematics. So it's interesting that exactly the structure that Einstein needed was exactly this marriage of these two very new branches of mathematics. So anyway, um, so it's not. I mean, I'm not saying this to take away anything from Einstein as the founder of general relativity. Certainly, he's certainly the founder of general relativity. But it's just to emphasize that it was founded on the basis of a very modern at that time mathematical prehistory, and it's amusing to recall that Einstein himself, when he first learned about Minkowski's reformulation of his special relativity, he rejected it. And only a few years later, to his credit, he realized that no, actually, this is exactly what I need. So, anyway, I also, let me encourage people who are interested in learning more about the birth of general relativity. This is actually one of the best documented episodes in the history of physics. Exactly because, we have many sort of primary sources, in particular Einstein's notebooks from that period. So one can really reconstruct, how it happened. This is not the case, let's say, even with special relativity. It is quite mysterious, how Einstein came to write his paper on special relativity and what exactly he was, what he had read, it's a bit mysterious. But with general relativity, everything is sort of very public. And so it's a wonderful story to read about. And there are many layers of that story, and certainly in this presentation, which is not really about history per se, it's more as you'll see, I'm just giving these episodes as examples. But if you're interested in the history, then there's really many layers of that, and it's very interesting to read.
But what about the Cuban students?
Can I? Oh, sorry.
Yes, go.
So thank you. First of all, thank you very much
Thank
for
you, Professor.
Can I? Sorry, am I interrupting someone?
No.
Okay. First of all, thank you very much for a very interesting take, because I have very limited knowledge in GR. I'm embarrassed to admit. So all of this is very refreshing for me. I find very hard, even though I sort of can maybe understand and appreciate the mathematics, I still find that one statement, that space dictates curvature of space, very hard to wrap my head around. And I was just, I guess, I mean, it's also because of my lack of my understanding of the subject that I really find it very revolting and difficult in my brain to capture it. Maybe you can help us somehow appreciate it in some way. There's some kind of, I don't know, I know it's non-trivial, so that's why it cannot be intuitive very easily, but still I'm a bit struggling with that statement. Maybe it's completely from my side, but I was hoping.
No, and I'm glad that so I purposefully said it like that in order to spark people's attention. So this is in some sense a pun on. So Johnny Wheeler, my academic grandfather, had famously described the Einstein equations as being that space that matter tells space how to curve, and space tells matter how to move. And so this is, if you want, an adaptation of Wheeler's phrase that actually space itself also tells space how to curve. So how does that work? Well, the point is the following. Let's go back to the apple. Okay, so this is sort of the apple. The apple is matter. It's sitting on, in this depiction on whatever, on space-time and it's curving space-time. Okay. So the point, however, is that effectively, if space-time is a little bit curved, okay, then that curvature itself acts like an apple. It's like having another apple. Okay? And that other apple is the curvature of space-time itself. So you can think, if you want, that so this curvature propagates as gravitational waves. So gravitational waves themselves, they act as matter. So they source the equations, just like if you had some sort of matter wave, if you had electromagnetism, if you had whatever your favorite sort of, you had a perfect fluid, which again sort of propagates by a wave equation. These source gravity. Well, gravitational waves themselves, they also source gravity. So it's as if.
So we should think of it something, we should somehow imbibe this in a way that it is intrinsic to the space itself, that there is this curvature. I think so. The problem is that most of us associate curvature with matter, and then even though I understand your statement, I never probably in the past thought of it very deep, and suddenly now I have this realization that, okay, how does this make sense? So I guess we need to understand that this is intrinsic to the space.
Yes, exactly. So curvature is something you can talk about. There's no matter. It is indeed, it's precisely as you said it. You should think, this is exactly the notion that Riemann introduced in the concept of Newtonian geometry. If you have a space with some metric, you can associate this notion of curvature. And I should emphasize that even before we look at the vacuum case, so let's go back to the general form of the Einstein equations, okay, which are here. You see them on the slide. So on the right-hand side, whatever this is some tensor, okay, but you really should think of this as the. I mean, I don't know if I can write with these tools, and I don't have my. I can try to. I don't have my. Okay, well, let me try to write something. Okay, so you can really think of this as the generalization. Okay, can you see this?
Yes,
Okay.
I can see.
Okay, sorry that because I'm really. It's a shame I don't have my. Okay, can I make that? Yeah, that's perfect. All right, I'm getting there. Okay, can't quite make a me. Okay, there we go. So this is really the generalization of the Poisson equation of Newtonian gravity. Okay, so the right hand side, whatever it is, it's the analog of the mass density of matter. And actually, why is this a tensor? Why is it not just some scalar? Well, it's exactly special relativity that tells you that whatever is on the right-hand side of this equation, it can't possibly just be the mass density, because special relativity tells you that, well, you can't talk about mass without talking about energy. And if you think about special relativity of fields, well, you also have to talk about momentum. You cannot talk about them separate. So it's not surprising that on the right-hand side, there's this complicated tensorial expression. The principle of special relativity tells you that. And in fact, those are exactly, in some sense, it was really the right-hand side of this equation that led Einstein to the left-hand side. But what is the left-hand side? So the left-hand side. Let's see if I have these tools again. So the point is that this thing on the left-hand side, it's not the full curvature tensor, it's a trace of the curvature tensor. So you should remember that these equations, sometimes, okay, in popular books, this is not said accurately, which is, okay, reasonable for popular books, but okay. But not in the context of this talk. So, so sometimes it's said that, oh, the curvature is equal to the sort of the matter density, but it's not the curvature, which is it's some part of the curvature. Okay, so in particular, some part of the curvature is not constrained directly by the equation. So if we now pass to the vacuum case, okay, so in the vacuum case, the equations, they take this form, right? So these equations say that part of the curvature is 0, but they don't say that all of the curvature is equal to 0, because this Rij, this is the so-called Ricci curvature, and this is a trace of the curvature. So it's just part of the curvature. Okay. So so anyway, so now again, this is not dissimilar to at this point. This is not dissimilar to the case of Newtonian theory, where if you're outside of the support of the let me write this here. So if you're outside the support of the mass density, then Laplace phi equals 0. But that doesn't mean that phi equals 0 there. That just means that Laplace phi equals 0. So that's why we feel gravity, even if you're in space, okay? You certainly move in a non-trivial way on account of gravity, even if you're not in sort of in the support of the mass density of matter. Okay. So that much is actually quite similar. What's very interesting, however, in general relativity is that there can be no matter anywhere. Okay, that's to say, this curvature can be 0 everywhere, and yet you can still have non-trivial solutions. That's a difference with Newtonian gravity. Okay, so so anyway, so that's sort of an interesting aspect of general relativity, which in any case will be useful for this talk, because in this talk I'm really only going to discuss vacuum general relativity.
But again, I don't want to be whatever you want to call me. But let's ask. Let's allow the Q&A students to ask first. Benny, Diana, Oris, Jose, Miguel. Is everything clear to you? Do you want to ask something? Don't be shy. Come on. Or think about it and ask later. But I want to force you to ask. Okay.
Well, anyway, I can continue, and there at any point, Also, I'll say more, and hopefully this will prompt further questions or discussion. Okay, so that was the birth of general relativity. So now I want to pass to the mathematics of general relativity, and I'm going to begin with what I could call the elementary mathematics of general relativity, which is sort of finding explicit solutions of that equation, Ricci equals 0. And even though in some sense this is, from the mathematical point of view, elementary, these explicit solutions, as we'll see, are absolutely fundamental in the theory. Okay. And the story begins at the very beginning, namely with Schwarzschild. So this is the famous paper of Karl Schwarzschild. I don't know if you can see the date here. If you can, this is actually January 1916. But actually, the contents of this paper were sent to Einstein. It was Einstein who actually communicated this paper for publication. But the contents of this paper actually were sent to Einstein in a postcard in December 1915. And if you remember his formulation of the equations of general relativity, let's go back here, it's November 1915, right? 25th of November. So this is literally sort of just weeks after in reality. So this is Schwarzschild, and in this paper you'll see this this text. So this is all taken from the original paper. Again, because I don't understand German, let me get rid of all the German text and just focus on this expression here. Let's make it bigger so we can actually see it. So the claim is that this metric, so this is a four-dimensional metric, this metric indeed satisfies Einstein vacuum equations, so that the Ricci curvature is equal to 0. So again, if you're a student just learning relativity, or sort of who wants to learn general relativity, then a very good exercise is to sort of, well, first of all, you have to learn how the Ricci curvature is defined. So that's, obviously an important exercise, so that you know what the Einstein equations mean. And once you do that, once you know what the Einstein equations mean, then it's a great exercise to verify for yourself, okay, that this expression here, so this alpha here is a parameter, so it's a real number, okay? So for all values of this parameter alpha, this expression here satisfies the Einstein vacuum equation. So this is a vacuum metric. Okay. So again, it's really remarkable if you think about it that this was discovered so early. Not because it's difficult to discover in principle. So how was this metric discovered? So this metric is very symmetric. So what does that mean? So this metric is stationary. In fact, it's something called static. Well, that basically means that it doesn't depend on time. Okay, but of course, because general relativity is a geometric theory, okay, you have to say that in a more mathematically precise way. And anyway, so the correct way to say that is that the vector field d by dt is a Killing vector field. But anyway, it doesn't matter. It doesn't. So this metric does not depend on time, but it's also spherically symmetric. Okay. So you can see that explicitly from these coordinates, from the way it's written. And again, okay, there's a more geometrically sophisticated way of saying that the group SO3 acts by isometry. But in any case, you can sort of read it off more pedestrianly, just explicitly from the form of the metric. If you recognize that this expression here is actually the standard metric of the unit sphere, where theta and phi are the standard spherical coordinates. Okay, so actually, in reality, it's not so hard to find this solution if you know what you're doing, because it's certainly very reasonable to try to find solutions which are very symmetric. And if you impose these symmetries, then this complicated equation reduces to actually a system of ordinary differential equations. And in fact, you get lucky and it all reduces to one ordinary differential equation. And moreover, you get lucky and you can actually solve that explicitly. And so that's what Schwarzschild did. Nonetheless, you still have to admire that, given the novelty of this theory at the time, because you see, now we're all used to, even in physics, we're used to sort of the notions that general relativity has bequeathed on us, sort of the notion of a space-time metric and sort of geometric equations and this and that. But you have to remember that at that time, this was something very new and very, very unfamiliar. So it seems sort of shocking that someone would have the courage to learn this theory very, very quickly, and moreover be able to sort of implement this procedure that I just said and find indeed an exact solution. Now it turns out that, okay, and I don't have time to really discuss the story of Schwarzschild, who really was a very remarkable scientist. He really was the person to do it, because he had actually speculated on sort of the relation of curvature of space and gravity long before himself. And he was very mathematically sophisticated. Even though he's often referred to as an astronomer, he was actually someone, you know, very mathematically sophisticated. And so it's actually not so surprising that he was the first to find an explicit, non-trivial solution of the theorem. So this is the first mathematical work, if you want, and it's just a few weeks after the formulation of the theory. Now, you already note, and we'll come back to this issue later, and I think for many of you, you'll be familiar with this or have some nodding familiarity with it, that this expression here is sort of funny. So remember, this alpha is a parameter, and actually the interesting case is when alpha is positive. Okay? Because so this was originally thought, and if you look at the title of Schwarzschild's paper, you'll see it. This was originally thought to represent the gravitational field outside of a point mass. That was sort of what this was originally supposed to be. And this alpha, this parameter alpha, in appropriate units, was supposed to represent the mass of that point particle. So that's sort of what Schwarzschild had in mind when he wrote this expression down. But if you look at this expression, you see that something funny is going on when r, okay, so r you should think of as some radius, when r is precisely equal to alpha in these units. Okay? Because then this denominator blows up, and it looks like this metric is sigma. So so anyway, this was in some sense the first non-trivial new discovery in general relativity of a new phenomenon, and this phenomenon sort of was already noted during the time of Schwarzschild, but actually was severely misunderstood by almost everyone at that time. And we'll come back to this issue later on, because this is precisely related to the notion of black holes. All right, so this is somehow the first explicit solution of the theory. Now it turns out that you might think that the topic of explicit solutions that you can write down in closed form would have exhausted itself very early, but remarkably, it didn't, and in fact, it took around 50 years to discover that this one parameter family of explicit solutions is in fact merely a subfamily of a larger family of, again, explicit solutions, which were discovered by Roy Kerr. Okay? So this is the celebrated paper of Roy Kerr. So you'll see the date. This is 1963. So it's really almost 50 years later. This is Roy Kerr, very deserving of the medals that he appears to be wearing in this picture. And this is his solution. Okay. So again, this is a two-parameter family of solutions. So actually, it's a little bit confusing because the notation is incompatible with the notation of the previous, but I wanted to keep the sort of pictures from the original papers. So what used to be denoted by A here, or alpha rather, this was a Greek alpha, is now denoted by M. Okay, so that's this M. And now there's a second parameter A. So this is a two-parameter family of solutions, and the claim is that when A is 0, this is isometric to the solution we just saw to the Schwarzschild case. So so anyway, if you want a hard exercise, okay, then you can try to check explicitly a posteriori that this metric indeed satisfies the Einstein vacuum equations. That's to say, it indeed is Ricci flat. So you're not going to gain so much by doing this exercise, other than a sense maybe of satisfaction that you can check on your own desk that indeed this celebrated expression is a solution of the theorem. So okay. So anyway, this was later understood to represent what's known as a rotating black hole. It turns out that this geometry obviously has similarities to Schwarzschild, but it also has some very important differences from Schwarzschild that we'll talk about later. Okay. So anyway, this is what I wanted to say about explicit solutions. And you can think of this, as I said, as sort of the most elementary, purely mathematical development in the theory. Maybe I should say a word about Kerr. So Kerr is still alive, and he's in New Zealand. But actually, he originally studied here in Cambridge, where I'm at present. And actually, his PhD was in sort of something algebraic. It was really sort of on the sort of, let's say, pure side of mathematics, and on the algebraic side, let's say. So he was not a student. So in Cambridge, there was actually a celebrated school in relativity. He was not actually a student coming from that school. So he was really doing something completely different, and something that, let's say, was quite algebraic. And actually, the difficulty in finding the Kerr solution was finally an algebraic difficulty. And maybe I'll just say a little word about this, more so because it's completely orthogonal to the type of mathematics that will appear in the rest of this presentation. You see, so why is there this huge disparity in the years? I mean, why was the Schwarzschild solution discovered immediately already in 1916, and why did it take 50 more years to discover Kerr? Well, you see, the reason, again, that Schwarzschild was discovered was that, well, assuming this symmetry is an obvious thing to do. And once you assume this symmetry, the Einstein equations reduces to ordinary differential equations. And, well, if you write that down, you'll see that it's not difficult to solve explicitly. So again, it was impressive that this happened only a few weeks after the theory was proposed, exactly because the theory was so different, was so new. But in reality, finding this was not difficult. But the Kerr solution is much less symmetric. So this solution, again, if you're sort of paying attention, you can see that it's still stationary. So it doesn't depend on time, okay? But it's no longer spherically symmetric. It's only axis symmetric. Okay, so here you see this phi. Okay, so the vector field d by d phi is killing, for those of you who know what that means. Okay, so this is the metric does not depend on phi, so it's axis. So you have, if you want, you have sort of two dimensions of symmetry. You have this time symmetry and you have this phi symmetry. So turns out that if you impose those symmetries and you look for solutions, that's not enough symmetry to reduce the Einstein equations to something a priori tractable. So in particular, this system of equations, which is a system of partial differential equations, and we'll hear much more about partial differential equations in just a second. I don't know what I just did, but sorry. So this system of equations, which is a system of partial differential equations, will not reduce to ordinary differential equations if you just impose that symmetry. Okay. So it doesn't seem a priori like you've made the problem any easier. So the reason that you can find such an explicit solution, it's actually quite subtle, and it has to do with various hidden symmetries that are present in, if you want, in these equations. And so the discovery of the solution is somehow connected to imposing, a fortuitous choice of sort of, if you want, of hidden symmetry. Anyway, again, this is a story with many, many interesting layers. The story of the discovery of the Kerr solution, and I don't really have time to say more. But again, for those who are interested, that's certainly something to read more about. Okay, so we'll go back to these solutions, because one of the themes that I want to give in this talk is that writing down a solution does not necessarily mean that you understand it. Okay, and in both cases of these two solutions, but especially in the case of the Schwarzschild solution, there was actually a huge time lag between when the metric was first written down explicitly and when the metric was understood. And so, and this will, if you want, this is related to the global geometry part of my presentation. But first things first, because I promised you that I like to think of mathematical sort of work in general relativity as passing through these three eras, which again, in this Hegelian framework, I think of as the thesis, the antithesis, and the synthesis, where the thesis is sort of what I'll call local PDE analysis. So let me pass to this, and we'll revisit these explicit solutions soon enough when I talk about global geometry. Okay. Is there any questions in the meantime?
People, questions? I am kind of following, I think. But what about the rest of you?
So I have a question. How come there hasn't been, as of yet, a somewhat easy derivation of the Kerr metric?
That's a very nice question. Well, I mean, okay, sort of the short answer is that, well, it is what it is. I mean, the sort of, the metric, that is the expression, the metric. It's not infinitely complicated, but it's not infinitely simple. And so, okay, it's not in that sense, okay, it's not surprising that, okay, any derivation of the metric will be painful. It's even painful, even if I give you the metric, it's painful enough to do this exercise that I just said. In particular, I think that it will take anyone, certainly the rest of this lecture, to do this exercise, namely just, given this metric a posteriori, to show that indeed it satisfies this equation. Okay, but sort of, it's not surprising given the level of complexity that you see that, okay, it's not, there's no obvious golden, there's no royal road to finding it. That being said, there is, I think, a missed opportunity in the story of its discovery. There is a particular way that I think it could have been discovered earlier than in Kerr's work, and which I think, in some sense, would have been conceptually easier. And remind me to say that later in this talk, because it's sort of it's natural to say it actually at some point later in this talk. Okay, well, let me go on. And again, always remember, I'm happy to be interrupted. So, okay, so the first period of, let's say, serious mathematical work in general relativity is in this domain, which I'll call local PD analysis. And in some sense, the main achievement of this era is this seminal paper of Yvon Choquet-Briard, then known as Fourier-Briard, proving the well-posedness of the Einstein equations. So this is Yvon, and this is her theorem. So let me sort of walk you through this theorem and try to explain its importance. And I really want to argue that, you know, you should really think of this result as somehow the fundamental theorem of general relativity. It's the thing that makes general relativity into a predictive theory. So let me tell you the statement, and then let me say a few words. Okay. So what Yvon Choquet-Briard showed back, and this was 1952, is that, you know, all the complication and the novelty of this equation aside, okay, in some sense, this equation is the quintessential, it sort of behaves like a quintessential equation of classical physics. And in particular, it satisfies that property that we come to know and love and sort of expect from classical physics, namely this property that initial conditions determine uniquely a solution. So the novelty of general relativity, notwithstanding that it's, you know, the theory is for a four-dimensional space-time with a Lorentzian metric and all that, okay, it still behaves like the quintessential of all classical theories, Newtonian dynamics, in that there is some notion of initial data, and it turns out that initial data in general relativity is described by space at an instant, okay, and there's a, you know, there's a technical so they're in more mathematical terms. So space at an instant is described by a three-dimensional manifold with a Riemannian metric, so precisely, you know, the type of metric considered by Riemann. But also remember, these equations are second order. Okay, if you write the Einstein equations in coordinates, you remember the formulae for curvature. Okay, then these are second order equations. And again, this is not surprising because remember, this is generalizing Poisson's equation of Newtonian mechanics, which was again a second order equation. Okay, so for second order equations, we should prescribe actually two initial conditions, sort of the initial position and the initial velocity. Well, for a metric, the initial position is just the metric itself. What is the initial velocity? Well, again, this is, if you know your differential geometry, so-called second fundamental form. So that's somehow the initial state, if you want. And well, there's a little subtlety also if you know your differential geometry, that if these are indeed going to be sitting in a Lorentzian four manifold, then they better satisfy some compatibility relations. So these compatibility relations are known as the Einstein constraint equations. Anyway, they're a nuisance, but in any case, that's the notion of initial data. And what Yvonne Choquet-Bras showed is that if you give me initial data, then there is a unique space-time which evolves from that initial data, okay? At least for a short time, okay? So just like in Newtonian dynamics, when if you give me an arbitrary, let's say in the gravitational context, so the force law is that of Newtonian gravity, if you give me an arbitrary collection of point masses with arbitrary positions and arbitrary initial velocities, then there is a solution, at least for a short time. Now, for a long time, things can happen, but particles can collide, etc. But for a short time, there's certainly a solution. So, so the same type of statement it holds for general relativity. So, if you want, it's really this theorem that makes general relativity into a sort of predictive physical theory. That's to say, it's because of this theorem, okay, that we can say, you know, general relativity predicts this, okay? Exactly because it's because of this theorem, okay, that we can say that, well, if the initial state of our space-time is such and such, then there is a unique prediction of general relativity that arises from that state, namely the space-time given by this theory. Okay? And so we can then compare physical reality with the prediction of general relativity, namely sort of this space-time, given, let's say, that we know the initial state. So somehow this, you know, without this theorem, if we just had the Einstein equation as somehow some equation, and we could write down some explicit solutions, etc., then it would be very difficult to talk about X or Y being a prediction of general relativity. Because, well, this is some equation, there are many solutions, there's this solution, there's that solution. You could always say, well, this solution is unphysical, that solution is unphysical, etc. It's really this theorem that tells us that that general relativity is makes unambiguous predictions.
But Michael, what do you mean with, first of all, why time in quotation marks, and what is sufficiently here?
Okay, so right. So why time in quotation marks? So of course, one of the difficulties even in formulating this theorem is precisely related to the fact that the Einstein equations, okay, unlike most equations of classical mathematical physics, okay, don't, you know, the Einstein equations, they don't have some canonical variable which is called t, okay? So, you know, if you want, so maybe it's a good point. Let me try to, maybe I'll try to write with, it would take too long if I try to do it by hand, so let me write here. Okay. Oh no, but this is, I can't write, okay, I'll try to write with this thing. So, so a good example of a more elementary equation for which this is true. So I've already told you the example of Newtonian dynamics. So that belongs to the world of ordinary differential equations. Okay? And actually the analog of this theorem for Newtonian dynamics was proven by Cauchy, and then maybe later also by Picard. Sometimes this problem is known as the Cauchy problem because of the work of Cauchy. But it was proven by, let's call it, 19th century mathematics. Okay? So one of the, you can say one of the big achievements of 19th century mathematics was precisely that theorem, to be able to say that you give me an ordinary differential equation, like the system of equations you get for Newtonian point particles. So you give me ordinary differential equations, and then you give me arbitrary initial condition. Okay, there's a short time interval for which there's a solution to the equation, and it's unique. So that's sort of a famous theorem in analysis. A second year student in mathematics would learn how to prove that theorem, and maybe in some countries, maybe even a first year student. So, let's pass to a more sophisticated case, but still more classical than general relativity. Let's look at the wave equation. Okay? So the wave equation is a partial differential equation. So let's see if I can write it. So it looks like this. So let me write it with my favorite signature. So minus dt squared of u plus Laplacian of u equals 0. So if you want, you can also try to show this theorem for this equation. So what's the analog of this theorem for this equation? This is just a theorem that you give me two smooth functions of x, y, and z. Okay, let's call them u0 and u1. Then there's a solution of this equation, okay, which at time 0 satisfies that u is equal to this given u0, and its time derivative is equal to u1. So that's sort of that's sort of an analog. Now that theorem for this equation here that I just wrote down, you can also prove it with very elementary mathematics, because this linear wave equation is so elementary that you can actually explicitly write down solutions in terms of it. There's a formula. And again, if you're a student and you want a classical exercise in PD, well, there's an exercise to do. Write down a formula for solutions of this equation. Okay. But now I'm going to make this problem a little bit harder. Okay. How am I going to make it harder? I'll make it harder as follows. So just a second. Let's see if I can make it harder. So I'm going to change 0, if I can do it. Let's see. Okay. So I'm going to write it here. So I'm going to change the right-hand side. So it's not 0 anymore. Okay. It's, let's say, this derivative squared. Okay. So this equation is already a lot more like the Einstein equations, because this is a wave equation. Okay. But we see on the right-hand side a nonlinear term. Okay, so this is dtu squared. And it turns out that because this equation now here is nonlinear, then you cannot write down the solution explicitly. And in fact, solutions will not exist for all time for this equation. Okay. So an exercise, which is actually maybe too difficult to be an exercise, but still you might want to imagine trying to show it, is to show that in general, if you put initial conditions to the equation, okay, then the solution will blow up in finite time. So okay, but here's the claim, okay, that still it is true for this equation here that given initial conditions, for small time, at least for small time, there is a solution. And this is where, if you want, 20th century mathematics comes in. Because you see, you can't write down the solution in terms of sines and cosines for general initial data. Okay? You cannot write it down explicitly. Nonetheless, using what's often called the qualitative theory of differential equations, you can prove that the solution exists. And moreover, you can prove some very important foundational things, like the solution depends continuously on the initial data. So we say that sort of this equation is well posed. And moreover, you can also prove certain things about the solution. So for instance, you can show that this equation here, this nonlinear wave equation, just like its linear analog, when you have 0, okay, satisfies finite speed of propagation. That's to say, waves in sort of which solve this system, they can only travel at the speed of light. So you can prove a mathematical theorem that encodes that fact. It's known as the domain of dependence. So, okay, to get back now to...
But is there anything... sorry, Michele.
Yes.
So this is dependent on the nature of the of coordinates, right? These wave coordinates, which are something like a harmonic coordinates. But I thought it was, maybe because I'm too naive, I thought it was a kind of very clever trick that she used to prove her theorem. But is there anything intrinsically special to those coordinates that, I mean, how do you pose this result physically? Or is it just because it's a nice and smart way of solving or proving the theorem that occurred to her?
Okay, so it's a good question, and this sort of brings me to, okay, so let's go back now to this equation. Okay? So it turns out that secretly this equation here, Ricci curvature equals 0, looks a lot like this equation. And in order to see this, you have to choose a smart system of coordinates. And this was, if you want, this was a source of a lot of confusion in the history of relativity. So you see, here's sort of the funny point. And okay, I apologize if for just 1 minute I say some things which are maybe understandable more for the experts. I'll go back to some more elementary things in just a second, but it's maybe worth making this point for some of the experts. You see, this equation here is geometric, and what that means is that if you change coordinates on your manifold, well, the equation has the same form. But precisely because of that property, then this equation written in arbitrary coordinates can never be, let's say, hyperbolic. It will never look like this when written in arbitrary coordinates. Exactly because the coordinate variance that goes with the fact that this is a geometric theory tells you that this has too many solutions. Okay. So in order to prove a theorem like this, you have to pick a good coordinate system. And so one of the difficulties of this work was indeed picking a good coordinate system. And in fact, this was not first done by Yvonne Choquet-Bras. This had actually, these type of coordinates that you need in order to write this equation in a form like this, actually Einstein himself had first discovered these coordinates in the linearized setting. And then they were used by many people early on, including De Donder, Darmois, Stellmacher, some other people already in the 20th century. So, but what's funny historically is the following. Whereas Einstein was actually the first to look at these type of coordinates in the linear setting, and in fact, he showed that the linearized Einstein equations in such coordinates look exactly like this, with 0 on the right-hand side. And for that reason, he was the first to predict that general relativity led to gravitational waves. So this was already in 1917, the first version.
Mm-hmm.
But later on, he actually sort of took that prediction back. And the reason was this confusion as to whether anything you derived from a particular choice of coordinates had physical meaning. But you see, one of the things that in some sense was resolved by this theorem is that irrespectively of what coordinates you use to prove this theorem, so, and Yvon Choquet-Bras indeed used what are known as harmonic coordinates, the result, okay, so let me erase this, just a second, I can, maybe I can't. Well, it will take a while, but anyway, let's get rid of this. Okay. The result of the theorem, you can state it without referring to whatever coordinates you use to prove it. It's a coordinate invariant statement. It's a geometric statement. In particular, if you want, this theorem was the first resolution, definitive resolution of that debate in the physics literature, whether gravitational waves are real. Because, you see, this theorem tells you that the Einstein equations, intrinsically, they have a well-posed initial value problem, which satisfies the domain of dependence theorem. So if you want, you can think of this theorem as providing a concrete, objective mathematical realization of the fact that general relativity is intrinsically a wave theory. It's intrinsically a hyperbolic theory. So anyway, so yeah, I mean, I make this comment more for the experts, but I do think that it's actually important to emphasize, and it's not something which I think is widely known in the physics world. There are a lot of very nice, actually popular books about the story of gravitational waves that were written in the wake of the recent discovery of gravitational waves. And there's a lot of discussion about the debates concerning the reality of gravitational waves, and the role that actually the mathematical theory played in that understanding is not really emphasized. But I think that actually, it's not only that a posteriori you can see this theorem in this context, but I think that this appeared exactly in the 1950s during the period of those debates. So in reality, I do think that some of this understanding filtered into the physics community, even though its origin was not recognized. So this theorem is very, 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 very important, and it's also quintessentially a product of, let's say, the PDE analysis of the early 20th century. So remember, as I've now erased that model equation, that nonlinear wave equation. So you really can think of the Einstein equations as an even more difficult version than that equation. And already that equation, you cannot solve the general solutions explicitly. Yet mathematical analysis developed techniques in order to, even though you cannot write down the solutions, to prove that they exist, and moreover that they have certain properties. And these techniques are very interesting, and also the techniques are very inspired by physics. So in particular, one very important technique behind this theorem is known as the technique of energy estimates. So it turns out that there are generalizations of the energy concept. And we all know how important energy is in physics. Energy is an important notion when trying to prove theorems like this. And it turns out that, in some sense, the reason you can prove this local well-posedness theorem is that you can define certain generalizations of the energy notion. These are higher order than the usual energy. And you can show that this energy is controlled for a short time. And using that fact, you can show that, okay, that solutions, in fact, do indeed exist. So I don't have time to really try to explain that in any more detail, but I just want to emphasize that it's really, these were sort of sophisticated techniques that were developed by some of the giants of PDE theory from the early 20th century, people like Adamar and Schauder and Friedrichs. So these are sort of some of the giants of PDE theory from the early 20th century, and further developed by Leray and Yvonne Choquet-Bras herself in the proof of this theorem. So the other thing I want to say about this theorem is the following: that I think that sort of in up until maybe 20, 30 years ago, this theorem is something that would only have been on the radar of mathematically minded people in general relativity. And that was before the rise of numerical relativity. That was before the rise of sort of actually trying to solve the Einstein equations on a computer. And it turns out that solving the Einstein equations on a computer is very similar to, if you want, what we in nonlinear analysis of PDE do. That's to say, when we try to prove theorems about general solutions of the Einstein equation. And it's very similar exactly because we're both really solving the Cauchy problem. We're both really trying to understand what happens when you start with general initial data, okay, and you evolve the equations. Okay? So this theorem that says that the solution does exist and it is well behaved for a short time is actually fundamental for the fact that you can write down the Einstein equation, you can encode the Einstein equations on a computer and try to sort of numerically solve them to some degree of accuracy. And in fact, it's not only that this is not only true at the philosophical level, but one of the difficulties that you needed to resolve in order to prove this theorem, namely finding a formulation of the Einstein equations in coordinates which was well posed, well, it turns out you have exactly the same issue when doing numerics. So these issues of well-posedness, which, as I said, in the 50s, 60s, 70s, were things that would only have been discussed in a very mathematics environment, well, now they're on the radar of anyone who's doing numerical simulations of the Einstein equation. So anyway, so this fundamental theorem, it really now is fundamental not only in the logical sense, but also somehow even in the everyday life of many working scientists working in general relativity, even if they don't realize it. Okay. Are there any questions?
Maybe.
I have a question. So, from what I understand, the proof of uniqueness of existence and uniqueness is in some way constructive, I guess, via a limiting process. So, but if I remember correctly, the global problem is not constructive, because I read Yvonne's proof for the well-posedness of the global problem, and she uses Zorn's lemma, which is non-constructive. It only implies the existence of a global solution. I wonder whether there is some progress in that.
Yeah, so actually there is. Yeah, so I should say again, this is maybe a comment for ignore what I say if you don't understand what I'm saying. Let me say it like that. So if you go back to ordinary differential equations, then you'll remember that you you first show that there's a local solution, and that you show by Picard iteration, let's say. Okay? Again, this is 19th century mathematics. And then you can trivially, quote, maximalize that. So remember, maximalizing is not the statement that the solution exists for all time. It's just that the solution exists for as long as it exists. Okay. So again, when we learn our fundamental theorem of ODE, okay, we learn it in this maximalized form. You give me a general ODE, you give me general initial conditions. There exists a time, t plus, which could be infinite, it could be finite, which is the maximal time of existence. Okay, and moreover, okay, there's even a statement that if that time is finite, then before that time you have to leave any compact subset of phasors. Okay, so this sort of maximalization is actually a triviality in the case of ODE. Now, one interesting thing in the case of the Einstein equations is that it was non-trivial to maximalize this theorem. So remember, maximalizing does not mean to say that the solution exists for all time. It might not, and we'll get back to that soon. It's just to say that it exists for as long as it exists in an unambiguous way. So that maximalization was actually first done by Choquebras and Bob Garrosh in 1969. So that sort of, again, for those, you can ignore what I'm saying if it's not understandable. So they introduced this notion of the maximal Cauchy development. And to construct that, indeed, the original proof used Zorn's lemma. And this was very funny that it used Zorn's lemma because, well, again, I don't want to get into the subtleties of mathematical logic, but you see, typically Zorn's lemma is invoked when you want to construct an object which is very non-unique. So Zorn's lemma is, it's equivalent to the axiom of choice, and it typically is invoked to, when you prove that, let's say, all vector spaces have a basis. Okay, so for infinite dimensional vector spaces, this is a non-trivial statement, and it's very difficult to prove because, okay, there's so many infinite dimensional vector spaces so big that there's no way to name any particular basis. So that's sort of a standard result that does need the axiom of choice, and it's very strange that sort of a theorem that at the end of the day was concerning the existence of a unique object would appeal to the axiom of choice. But it did, in fact, the proof actually appealed twice to the axiom of choice. And this issue was debated by philosophers of science because, indeed, it gave the impression that the general relativity was not a constructive theory, and what does this mean, etc. So actually, a former student here in Cambridge named Jan Zbierski, so he de-Zornified the proof. So he actually came up with a constructive proof of that result. So it no longer is living in that limbo. So we can all rest. We can all sleep peacefully now in the knowledge that general relativity is a constructive theory.
Okay, thank you.
Okay, maybe I should ignore what you just said because probably I didn't understand anything. But
that's perfectly fine.
Is what Costa said, is this again related to what I was asking before about the choice of wave coordinates, which are
no, this is a separate issue. This is, yeah, I mean, this really is a separate issue.
Because this is what leads you to formulate the Einstein equations as hyperbolic partial differential equations, which is what I think you were mentioning is the Cauchy problem, which can be locally solved for some initial data, but locally. But anyway, maybe you just continue talking, and we'll try to find out what I don't understand later.
Okay. Yeah. Let me not. say more about that simply because I mean, it's not so difficult to explain in the end, but it will take us on a little bit of a tangent. All right. So this was somehow the first current, let's say, the first wave of highly non-trivial mathematical work in general relativity, the local PD analysis, which I hope to have argued is absolutely fundamental in how we view general relativity as a theory. Okay. So that's, if you want, what I'll call the thesis. Okay. And now let's go to the sort of a second and largely orthogonal current of mathematical work. Work centered on the study of global geometry, so a very different type of mathematics. I'll call this the antithesis, if you want, and then we'll see sort of how these two currents of mathematical work come together in more recent sort of study of the ancient questions. Okay, so global geometry. So remember, let's go back to our discussion of Schwarzschild. So remember when we discussed the Schwarzschild metric, then when this parameter a was equal to r, it looked like the metric was singular. And there was a lot of debate about that at the time. So we're talking the first years of general relativity, the years immediately after 1915. And there was somehow a lot of confusion, and essentially everything that everybody said was incorrect. And the people were very brilliant people, the people concerned. So we're talking about Einstein himself. We're talking about mathematicians like David Hilbert, many people. But it turned out that actually there was a very simple resolution to what was going on when r is equal to a, and this was found actually by Georges Lemaitre in 1932, but did not become very well known in the physics community at that time. So what Georges Lemaitre discovered is that if you take the Schwarzschild metric and you change coordinates in a rather elementary way that I don't have time to show you explicitly, then the metric takes this form here. And the thing to notice about this form here is that when a is equal to r, nothing blows up. Okay, so these coefficients here, okay, are fine when a is equal to r. They don't blow up. This coefficient here vanishes, but that's fine in the Lorentzian metric, and we'll understand what that means in just a second. But nothing is blowing up. So this singularity that appeared to arise at r equals a in Schwarzschild was actually a coordinate singularity. It was much like the singularity of the well, you see, it's sort of ironic. If you look at this expression here, okay, there's a coordinate singularity at theta equals 0. Okay, no one was ever confused about that, however, because everyone knew that when you write this expression here, you really mean theta and phi to be coordinates on the sphere. Okay, and it turns out that an exactly analogous thing was going on with the previous metric expression at r equals a. But because people didn't know from before what was the correct underlying spacetime, they didn't realize that. So this was really realized by Georges Lemaitre. But it turns out that the way to visualize, to understand a Lorentzian manifold, to understand its geometry, is to draw the light cones. So to draw at each point the tangent vectors that have 0 length with respect to the Lorentzian metric. Have 0 length with respect to this, and so I've depicted that here, okay. And just to sort of guide you to this picture, you see, so you're to imagine this picture. So this coordinate taf is like, you think of this as like t. So this Greek taf. So So this is the direction of the vector field d by d tau. Okay? And d by dr, okay, on the other hand, is pointing in this direction, in this picture. Okay? So it's a radial vector field. Okay? So it's pointing out, and you think that this picture is going around. Okay, but of course, I have to draw something on the screen. So okay. So what do the light cones look like? Well, if you go out to large values of r, you'll notice that this metric becomes like the Minkowski metric, because, you know, a is some constant, some positive constant, so a over r goes to 0, so this becomes -1, this becomes 0, this becomes 1, so you're left with minus d tau squared plus dr squared plus r squared d theta squared plus sine squared theta d phi squared. And again, a good exercise for students, this is just the Minkowski metric in spherical coordinates. Okay, so and of course in Minkowski space, we started this talk with Minkowski space. The cones are like this. They're upright. Okay, so when you're far away, the cones are like this. Okay. So what happens is you go to smaller values of r. What you can convince yourself is that the cones are turning inward. And in particular, let's go all the way to r equals a. Okay, then this vector here, d by dt on r equals a, is in fact null. And you can read this all from the metric. And again, this is a good exercise to think about this if you're learning about Lorentzian metrics and geometry. So if you look at this coefficient in front of the term d tau squared, okay, so if you look at this coefficient here, well, this vanishes. So what does it mean for this coefficient to vanish? It means precisely that this vector, d by dt, on r equals a is null. And null means it's tangent to the light cone. So this is consistent with what I've drawn. The light cones are now tangent. And now if you go further in, well, they've turned even more. So this is the geometry. This is the picture of the global geometry of Schwarzschild space. So what does this all mean? Okay. Well, we can say what it means in the language of two observers. So observers in general relativity, by definition, they follow what are known as time-like curves. So these two curves are examples of time-like curves. And time-like curves are simply curves whose tangent is always inside the light. So the relevance of this r equals a is as follows. If you have two observers as depicted, one which crosses into the region where r is less than a, and one which doesn't, then you'll notice the following fact. The first observer, this observer who eventually crosses into the region r less than or equal to a, before he or she crosses, he can send a signal to the other observer. Okay, and the reason he can send such a signal, you see, signals they propagate tangentially to the null cones. So this is another postulate of general relativity, that if you have a photon and you look at its tangent vector will be tangent to these light cones. Okay, so I've drawn an example of such a photon trajectory. So as long as the observer is outside, he or she can still communicate with, let's say, another observer who's outside. But once this observer crosses this boundary, so let's say the observer's at a later point, if you look at all the signals that the observer sends, okay, the light cones have tilted so far that these signals are forced to go to smaller and smaller values of r. So as a result, this observer can no longer communicate with, let's say, this observer. So this is exactly why we call this region black hole region. Okay, it's a region of spacetime that cannot send signals to observers which are outside. And the black hole region is what we call the event horizon. So So what I want to emphasize is that this notion of black hole, is a purely geometric notion. It's a purely global geometric notion. Okay? And it took a long time to be understood, and wasn't this language that I'm using is actually language that, in some sense, was things were said in this way explicitly only in the 1960s. Okay, but this is exactly the black hole concept. Okay, so this explicit Schwarzschild solution, the first solution to ever be written down explicitly, was hiding this highly non-trivial global geometric property. Okay, except that this property, in order to understand it, you first had to, resolve that coordinate singularity that had confused everything. Okay. All right. So understanding this was a huge sort of mathematical accomplishment in itself, which really belongs to the domain of global Lorentzian geometry. Okay, but there's more that one can say, because it turns out that the Schwarzschild solution does have a singularity, except that singularity is not where people were focused on, was not at r equals a. R equals a was just a so-called event horizon. But it has a singularity where r is equal to 0. Okay, and it truly is a singularity. In particular, the curvature blows up there, for instance. So it is certainly a singularity in some real sense of the word. Nonetheless, we're very familiar in physics with with instances where we have some mild singularities, and yet we still consider the solutions, and we still, if you want, continue the solutions beyond the singularities. After all, point masses, right? You can think of those as sort of singular solutions, but we still somehow consider these solutions, and we still consider the region which is affected by the singularity. So naively, you might think that the solution here is similar. And in fact, the first person to really pose these questions is J.L. Singh, and this is taken from a paper that actually was submitted, if you'll notice the date here, in 1949. So Singh is actually the first person to discover the maximal extension of Schwarzschild. I'm here not talking about the maximal extension. I'm talking about only Lemaitre's extension. So the maximal extension is often attributed to Kruskal, who also studied it and found a very nice system of coordinates covering it. But the first person to discover it was actually Singh, and this was 10 years before. And in fact, Singh was really, I think, the first person to take a manifestly geometric approach to general relativity. So in particular, all these depictions that you see here with the cones, etc., there is a sense in which they really owe a lot to the influence of Singh. And so Singh was really the first person to talk about this singularity inside Schwarzschild, and he was the first person to ask the question, well, okay, suppose you have this observer who falls into the Schwarzschild black hole and reaches r equals 0. Is it conceivable that he or she could travel right through this singularity? Okay? And these are words taken from his paper. So he actually suspected that the answer was yes, but it turns out that the answer is no. And this is something that we understand now rather well, and we understand why. So what actually happens is that this observer is him or herself torn apart by infinite tidal deformation. So what does that mean? Well, let me first show you the picture and then say it in a more formal way. So if this is the observer, okay, then as he or she falls down, okay, he fell into the black hole, he or she is approaching r equals 0, and you notice that he or she is being deformed and now he or she is even more deformed, and now, okay, he's completely infinitely deformed as they approach r equals 0. So so this was first really discussed actually in the famous textbook Gravitation of Misner, Thorne, and Wheeler. In this chapter, The Fate of a Man Who Falls into the Singularity at r equals 0. This was written back in the 70s, and back then it was only men who could fall into singularities. Now that's no longer the case. So, so actually, this this picture has a precise geometric meaning that could have been discovered by Singh, and in some sense should have been, because he was actually the first person to study the second variation formula in Riemannian geometry. But somehow the way you formalize this is, if you think of an observer, okay, observers have arms and legs. So this is an arm of an observer, and this is a leg, okay? And the arms and the legs, how do they propagate in a freely falling observer who falls along a geodesic? They propagate as Jacobi fields. So basically the statement here is that depending on how they are oriented, Jacobi fields along such a geodesic, they blow up or they go to 0. So this is somehow this is the statement, and this is sort of what it means for the observer to be crushed. So I want to emphasize that this is a much stronger statement than the statement that the curvature blows up. So the curvature blowing up per se does not imply that observers are destroyed. Okay? And this was very well realized by Singh. Okay? Just because the curvature blows up does not mean that observers are actually destroyed. So it turns out that observers are destroyed in Schwarzschild, but it's really because there's something much, much stronger happening. And in fact, there's another way of saying this statement that actually was only recently shown by Jan Zbierski. This is the same person who I mentioned earlier, the person who desornified the local well-Poisson's theorem of Choquet-Bras and Bob-Garrosh. You see, again, this is a comment for experts. The fact that the curvature blows up is morally equivalent to the statement that you cannot extend this metric as a twice differentiable Lorentzian metric. But actually, the fact that sort of observers are destroyed, that is morally equivalent to the statement that you cannot extend this metric merely as a continuous Lorentzian metric. And that's sort of what Jan Zbierski showed. So the upshot of this discussion is that inside this black hole region, there is a very, very strong singularity, and all observers who fall into that singularity, they are actually destroyed. Okay. And again, all these statements are statements of pure sort of, let's say, global geometry. So anyway, this is a very nice thing to learn about if you haven't. So learning about the Schwarzschild solution, learning about its geometry, it's very nice because this all seems like science fiction, but all these things are correspond to very precise and purely geometric statements. Okay. So, and I can give people references later on. Okay. So. So
Sorry.
Yes.
Can I ask one small question?
Yes.
So if I just can repeat what you meant, you're saying that these Jacobi fields, which are basically what the observer is what exactly the tidal deformation is, right? So you're saying that they are all these things overlap.
Yeah.
Okay. So.
Yes.
Okay.
Yes.
I just wanted to be sure that I'm happy.
Yes.
Okay, thanks a lot.
Okay. So this is the case of the Schwarzschild geometry, and all this is very nice. This has, very what at first seemed like very bizarre behavior. You had this black hole region, you have the singularity, and you have these observers who only live for finite amount of time and are crushed in this way that I explained. And the common point of view when this was first understood, so again, we're talking about the 1950s, the early 1960s. So the common point of view is that all this is fine. This is some explicit solution that has this property. But this was a very symmetric solution. That's why it was discovered. That's what I told you at the very beginning. It would not have been discovered had it not been so symmetric. And, you know, it's not unheard of in physics that very symmetric solutions, they have some singularities because of their symmetry. Okay, and they are very special because of their symmetry. And so it was widely believed in the relativity community, including, it seems, by Johnny Wheeler himself, for instance, that all this pathology, okay, and it was very much thought of at that time as pathology, would go away once you perturbed this solution. So this was very much the expectation, and this expectation was completely debunked by a spectacular theorem due to Roger Penrose that came onto the scene in 1965. And again, you'll see this. I guess this paper was received in 1964. So this is the paper that Roger Penrose got his Nobel Prize for this past year. And this is the paper cited by the Nobel Prize Committee. And quite remarkably for a physics Nobel Prize, this paper is a mathematical paper. This paper is a paper which proves a theorem. And so I'm going to show you this sort of theorem just now. It's, if you want, it's the crowning achievement of this era that I'm describing now of the subject, namely the era of global geometry. And actually, it's a very elementary mathematical theorem in some sense. So, well, this paper was only 3 or 4 pages. It was a PRL. Of course, okay, strictly speaking, the paper didn't have the complete proof. So the complete proof was sort of published a few years later by Penrose in other venues. But the fundamental ideas of the proof are already in this paper. So what's the theorem? So this is, if you really want to point to the influence of mathematical work in general relativity, sort of the profound influence of mathematical work in general relativity, and point to one theorem, this would be it. So what is the theorem? So the theorem says the following very simple thing, and I'm actually specializing the theorem to the context that I'm talking about, namely vacuum general relativity. So the theorem says that any solution of the Einstein vacuum equations, so any spacetime satisfying these equations written down by Einstein, which moreover arises from asymptotically flat data, and in astrophysics, that's always what we're interested in. We're interested in spacetimes that evolve from initial configurations that are isolated. Okay, so that's exactly what this mathematical assumption means. Okay, and moreover contains something called a closed trapped surface. So this was a geometric notion that that Penrose introduced, and I don't have maybe time to explain exactly what that means, but suffice it to say that the Schwarzschild spacetime contains such a closed trap surface, but also any spacetime which is close to Schwarzschild also contains a closed trap surface, and you can argue that very easily. So the theorem says that any spacetime with these two properties is necessarily geodesically complete. So if you thought that all these properties would go away if you perturb the Schwarzschild solution, what Penrose's theorem is telling you is that, well, no, unfortunately, in some sense, the first bad property that you realize, namely that there are these geodesics, like such a geodesic here, which only lives for finite time. Okay, so such a geodesic like this, which only lives for finite time, that's not going away. Okay, so something about this pathology, at least something about this pathology is stable to perturbation. So I cannot exaggerate how important this theorem was for our understanding of general relativity, because if you want, it changed completely the point of view on the role of the Schwarzschild solution. So whereas the Schwarzschild solution originally was thought of some explicit solution, but some very symmetric explicit solution, which was completely non-indicative of general solutions, this theorem told us that this aspect of the solution, namely its incompleteness, okay, is actually stable to perturbation. So so this played a very, very important role in the physics community and the astrophysics community. Typically, the astronomy community, especially at that time, was a very conservative community, not one to accept new notions so readily. It was really this theorem that led to the acceptance of the Schwarzschild solution as something which was not necessarily a pathology, and thus, in particular, the acceptance of the black hole notion. Okay, and now it's unthinkable to study astronomy without the black hole notion. So in the current picture that astronomers have of the observable universe, black holes play an extremely important role. Okay, so so this is really an extremely influential theory. So so I want to make a comment. So this theorem is typically known as the Penrose singularity theorem. I've actually chosen to call it the Penrose incompleteness theorem, and the reason is the following, as you'll see. So so we just discussed what the geometry of the Schwarzschild solution looks like. Let's think about the geometry of the Kerr solution. Okay? So it turns out that the geometry of the Kerr solution is even more bizarre than the geometry of the Schwarzschild solution. So when you're far away from the black hole, it's actually quite similar to Schwarzschild. So again, you have the light cones, which are more or less upright. Okay? And just like in Schwarzschild, as you move in, so as you move to smaller values of r, the light cones, they turn and they become tangent to some null hypersurface known as the event horizon, and then this region here. Sorry, let's see if I can use my tools. No, it's not. So well, maybe I'll give up on trying to draw with this. Maybe okay. So this region here is again a black hole region. Okay. Let's try to shade it in. Okay. So that region again, I'll erase that in just a second, is a black hole region. Okay. But let's look what happens inside the black hole region. So remember, inside the Schwarzschild black hole region.
Can I interrupt, please?
Yes.
Could you just please go over it again? I just lost you there for a bit.
Sure. So let's go back. So what I was saying is the following. If we look at the geometry of this cursor, so this is the Kerr metric that I wrote down. I'm not going to show you again the form of the metric because it will not help us in this discussion. You have to believe me when I explain the geometry because it's very difficult to read from that form. Okay. But my claim is that if you look at the light cones of this geometry, okay, they behave as I'm describing them. And I'm trying to describe them, starting from large values of R. So think large values of R means over here and over there, okay, and going in. So at large values of R, so we can see them here, okay, the cones are more or less upright. They're like in Minkowski space. And as you go in, so as you go in this direction, okay, they're turning, okay? And so there is, just like in Schwarzschild, a null surface to which they're tangent. And this I'm calling the event horizon, okay? And just like in Schwarzschild, what this means is that if you look at the region of space-time, which is inside of this, okay? And unfortunately, I don't know how to bring that to the back or something like that. So I'll just put this black thing here. This region of space-time cannot communicate with the outside, okay? So this is exactly the same as in Schwarzschild. So we have this region here of space-time. Because of the way the cones are oriented, the signals do not go to the outside. Okay. So that much is the same. So from that point of view, the curved space-time has very similar geometry to Schwarzschild. But now let's look at that region inside. Okay. And now here's the funny difference. That whereas in Schwarzschild, what we saw is that observers who went in, okay, they reached in finite time this singularity, which completely destroyed them. And again, that's a formal mathematical statement. You can look at Jacobi fields. They blow up or go to zero, whatever. In the curved space-time, that's not what happens. And in fact, what happens in this type of depiction is the following. These light cones, they keep on turning, and they turn all the way around, okay, like it's depicted. Which means that if you have an observer, so here's an observer, okay, and you look at their trajectory. So observer is now inside the black hole. Observer is approaching this other surface. Observer has reached this surface. So before encountering anything singular, the observer crosses this surface. So this surface is known as a Cauchy horizon. And actually this terminology is due to Stephen Hawking and first appears in this paper here from 1966.
Okay, so this is the continuation of what Michalis began the other day, and Kostas, who I consider to be my third son, child. I have only one son, so my second son, adoptive. We are working on the paperwork. Is going to talk about constructing quantum physics, because he has seen a couple. We have been discussing, and he has seen a couple of interesting things which don't seem to make much sense. So, Costa, enlighten us, please.
Okay. So let me first introduce myself a little bit formally. My name is Kostas Tzanavaris. Unlike the previous talker, Professor Dafermos, I'm a master's student at the University of Athens, so I would hope that this encourages people to interrupt me constantly.
And I'm going to interrupt you. It was a very formal introduction.
Exactly.
I don't know what you're talking about.
So I will begin by explaining how quantum mechanics, as you understand it from your undergraduate lessons, emerges inexorably from a few physical arguments, mostly based on symmetry, using a number of theorems of functional analysis and harmonic analysis. Hopefully this will correct many misconceptions you might have from these undergraduate courses. This is the first part. The second part, I will actually present a scheme on how this method can be applied to construct quantum field theory. Essentially, quantum field theory emerges from symmetry plus causality on a Minkowski spacetime. And this will actually show you how some very fundamental concepts, like, for example, what is a particle, actually kind of fails when you introduce non-trivialities like a curved spacetime. So let's begin by discussing for a few minutes the basic axioms of quantum mechanics. From our experience, we know that in microscopic phenomena, a physical observable, like, for example, the energy, can either have a discrete or a continuous spectrum. Does anyone understand this statement?
That's a very, very good question, actually. Students speak, or some heads will start to roll.
For example, do you know the Balmer series for the hydrogen atom?
I do.
Okay, so I hope you're familiar with the Bohr model, where energies for the electron orbiting around the nucleus are quantized. They take discrete values, and this was postulated on the discreteness of the emission spectrum of the hydrogen.
Yes, the Balmer series describe the energy that finish in the second level, I think so.
Okay, yeah, there are actually a lot of phenomenological series like that, but I just wanted you to have something concrete regarding the discreteness. But you can also, energy can have a continuous spectrum when you're doing scatter. I'm sorry. When you're doing scattering experiments, you can have a continuous spectrum of energy. So the problem is formulating a mathematical framework in which you can have a discrete and a continuous spectrum.
Costa, can you explain that a little bit better? What do you mean? You can have a continuous. What did you say?
Continuous spectrum, energy
spectrum
spectrum.
of energy by doing scattering experiments.
Yes. Well, the energy of an electron, free electron, in a scattering experiment, it can have a continuous. It can take continuous values.
Yes.
Okay, so you have a system that can take a physical observable, to be exact, that can take both discrete and continuous values, right? So how do you describe this mathematically? The answer comes from functional analysis, and this was actually the work of John von Neumann in his book on the foundation of quantum mechanics, in which he formulates, in which he models quantum mechanics by assuming that the state space is a Hilbert space, and every observable is represented by self-adjoint operator. Is everyone familiar with the spectral theorem in linear algebra? I ask the students, of course.
Okay. Since they are extremely shy for some reason, I'm going to say I don't know what it is.
Okay, so the spectral theorem in linear algebra basically tells you that you can have a basis of orthogonal vectors who are eigenvectors of a self-adjoint operator. A self-adjoint operator has an important property that its eigenvalues are real. So we use self-adjoint operators because in an infinite dimensional Hilbert space, they can take both continuous and discrete values. Okay? Is everyone on board with that?
Yeah.
Yes.
Okay, so that's the first characteristic of microscopic phenomena. The other characteristic of microscopic phenomena is randomness. In a sense, you cannot predict the outcome of a measurement. So for reasons that at the moment are not yet clear. So the problem is how do you make, so the state of a quantum system must be described by a probability distribution. Do you understand why is that?
Why?
Okay. I guess this is Stamatis, so this is an inflammatory question.
Yeah.
Okay, so since you cannot make a deterministic, as of yet, measurement, you are always calculating probabilities. The only the only measurable quantities must be determined statistically. So what you have is essentially a probability function, probability measure. In the late 30s, Feynman and Birkhoff wrote a paper on quantum logic showing that measurements can be identified with subsets of, with closed subsets of the Hilbert space. This is, he called this lattices.
Is this true for the deterministic models of quantum mechanics also?
Yes, so this is another question, is whether you can have deterministic models being, how do you say this, being compatible with this, this model. But yes, this includes deterministic models, but then you have to give up locality. But this is another topic that I don't want to get into that much because we'll run out of the time. So the problem is, how do you go from a probability measure to the usual Born's rule, which states that the probability amplitude for going from a state psi to a state phi is the absolute value of their inner product. The answer, this can actually be proven. It was proven initially by von Neumann, but his initial requirements were rather strong and not very well motivated. But Gleason, I think this is how you pronounce his name, proved a much less stringent theorem in the 50s. So you have almost all of quantum physics in two statements using very physical arguments. Empirical arguments, sorry. Is everyone on board with that? Questions? Okay, let's move on. Now, the second part is how do you determine the dynamics of a system? Say that you have a system prepared in some state. What will its time evolution be in, after a specific time interval? So, of course, we all know the Schrödinger equation, but how do we derive it? In most classical physics, in most of quantum mechanics courses, this is done by quantization. This is the mapping of quantum system, of a classical system to a quantum system, and which I will describe a bit. So let's go back to how the dynamics in classical mechanics is done. So a classical system is described by a Hamiltonian defined on its on a state space called a geometrical space called the phase space, and its dynamics are of course given by the Hamilton's equations, which are these. Can you see the cursor? Yes? No?
Yes.
Okay. This is, I assume everyone's been exposed to this at some point in their undergraduate year. So if you have a question, please stop me. Okay. So in a similar way, which is not very similar at the moment, the evolution of the state is described as Schrödinger's equation. It states that there is a self-adjoint operator called the Hamiltonian. Okay, this is it. This yields a unitary evolution. Is everyone okay with that? Can we move on? Okay, no questions. So the one thing in common.
Wait. So could
Yes?
you repeat the last thing? I kind of lost you.
So the evolution of a quantum system is given by a unitary transformation.
Okay.
Which is in turn given by the Schrödinger's equation. Okay? This is it. But the problem is, how do you derive it? Okay? Yes?
Yes.
Okay. So the time homogeneity of the equations imply that the time evolution of the system is given by a unitary by a one parameter group of transformation. The parameter being the time variable. Okay. So in classical mechanics, this one parameter group of transformations is a diffeomorphism generated by the Hamiltonian vector field, and it obeys these kinds of equations. Sorry, relations. Can anyone tell me maybe how this one could go about proving these identities? This is left as an exercise. I'll give a hint. It uses the uniqueness of the ordinary differential equations. The idea is that both this and this satisfy the same initial value problem. Okay. Do it as an exercise. I think it will help you understand it. Okay, so
Costa, by the way, you gave me or showed to me a list of exercises. What do you intend to do with that?
Yes, so I have I have given some exercise to Pau, and he will upload them later, I hope. This is to fill in the gaps in some of the things that I will say in this presentation, and have
okay.
some.
Because I thought you wanted the students to do those exercises during the lecture.
No, not during the lecture. I hope after the lecture they will read and do the exercise so that they will understand the material better, because mathematics cannot be done just by watching a lecture. Okay.
Okay. So I will upload it. So he just let me interrupt you for 1 minute.
Yes, of course.
So Costa has prepared a quite detailed list of exercises. He has put time and dedication into them. So please have a look at them. I will upload them later to the webpage.
Okay. Can I continue now?
Of course, you can do whatever you want.
Okay. So in quantum mechanics, the evolution of the system is pretty similar. You have a unitary operator taking the initial state, psi, to psi of t, which is the state after a time interval of t. Okay? And time homogeneity again implies that this one group of transformations obeys the same equation. Okay. So let's go to the concept of quantization. Quantization, as I said earlier, is a procedure by by getting a quantum system from a classical system. This is done by mapping classical variables like the position and the momentum to self-adjoint operators. And by substituting the Poisson bracket, remember the Poisson bracket? This is the definition of the Poisson bracket. Okay? To the commutator of operators. Can anyone tell me whether you find it satisfactory of an answer? There is no yes or no answer. I just want to hear your opinion.
I mean, it depends on whether. Can you reformulate your question? Because are you satisfied? I don't know. It is.
Do you find this quantization procedure satisfactory? I mean, why we use it?
But this is as it is per se is a mathematical definition. How do you connect it with?
So the idea is that. So myself, I'm not very satisfied with this substitution because I do not find really very reasonable.
Why don't you find it reasonable? I mean, I agree with you. I'm playing, I'm humoring you because I'm not hearing anyone speaking. But let's, play the game. Why aren't you satisfied with this?
Because I view quantum mechanics as more general than classical mechanics, and classical mechanics should be a limit of quantum mechanics. Using quantum mechanics, using classical mechanics to construct quantum mechanics seems to be getting it backwards. Do you understand what I'm saying?
No. What do you mean? What backwards?
Because quantum mechanics must be a more general theory than classical mechanics, right?
You mean that quantum mechanism must englobe classical?
Yes, the classical mechanics should be a limit of quantum mechanics, but the process of quantization means that what you're doing is taking it backwards. You need a classical theory to develop a quantum theory. Moreover, there is a mathematical result proved by Groenewald in his thesis that this is actually impossible.
Elaborate.
So if you try, if this substitution, mapping the Poisson bracket to the commutator is actually wrong, because it implies that there is an isomorphism between the Lie algebras. This is not the case.
This is actually the question. So where is this coming from? Is this just out of the blue?
This quantization emerged when we try to develop quantum mechanics at first, so that in the limit of h bar goes to 0, our equation would the evolution equation, Schrödinger's equation, would imply would have as a consequence Hamilton's equations.
Yes.
One of these, and all of them in some form or another relied on this. But this is impossible. There have been other quantization schemes, but like for the one that is used more often is by the Weil map, which does not induce an isomorphism between the Lie algebras. But in the limit of h bar goes to 0, it actually reproduces the Poisson bracket. However, there is another reason that I don't like quantization, and that is because it hides observables that are purely quantum. Can anyone think of a purely quantum observable? I asked the Cubans, sorry. Yeah, the quantum numbers seem like which. Okay, so this actually emerged as a consequence of the Schrödinger's equation. Something more fundamental.
Spin.
Sorry.
The spin.
Yes, that's the spin. That's actually very true. So if we don't approach quantum mechanics using quantization, how do we do this? How do we construct it without quantization? And the answer comes from symmetry. So in quantum mechanics, when you're doing very basic quantum mechanics, what you're calculating actually are the transition amplitudes, okay? So a symmetry operation, which is a symmetry operation is something that leaves these transition amplitudes invariant, right? Okay. So the problem for the moment is to how do we describe symmetries in quantum physics? And the answer comes from a theorem of Wigner. A symmetry operation in quantum mechanics is either a unitary operator, which is a linear operator satisfying this equation, or an anti-unitary operator, which satisfies this equation, and it's actually anti-linear. Okay? Continuous symmetries like rotations, translations, boosts, etc., form what we call in differential geometry a Lie group. Has anyone ever encountered this definition?
The definition of a Lie
group? Of a Lie group. Does anyone know what a Lie group is?
Because you just mentioned before a Lie algebra and a Lie
Yes.
group, and it would be important to note that there's a big difference between the two.
Yes. Cubans? Have you encountered the definition of a Lie group before? I assume not. So let me present a few examples. A Lie group basically is you can think of it as a geometric space, which is a group in such a way that the group operations are continuous, actually smooth. If you were talking about Lie groups, if we're talking about Lie groups like representing rotations, translations, boosts. So the most common the most common Lie groups are the orthogonal groups, which are the symmetry groups that preserve the origins. The groups that preserve the norm and also preserve the origin, or equivalently, they preserve the inner product. A generalization of these isometry groups are the Lorentz groups, which play a fundamental role in relativity and physics in general, because they preserve the Minkowski product. Minkowski product is just a space-time interval, okay? Another group, which I hope nuclear physicists know about, is the unitary group. The unitary group is the equivalent of an orthogonal group, but instead of preserving the real norm, they preserve the complex norm in complex vector spaces, okay? So some subgroups are the special. Some other groups is the special inner group, which preserves the volume, the determinant basically of vector spaces, and the special unitary groups, which are these subgroups. Preserve volume and the norm. Okay, so continuous symmetries. We will forget about anti-unitary linear operators because they represent they represent discrete symmetries like time reversal. Continuous symmetries are described by unitary operators because they must be connected to the identity continuously. Okay. So let's talk about representing these symmetry groups into a Hilbert space, which is a state space of a quantum system. Okay, so when we're talking about representation of a group, of a symmetry group, we mean that we require that these vectors, okay, these vectors are physically equivalent. Does anyone know when that happens? People? When are two unitary unit vectors are physically equivalent in quantum mechanics? So the answer is that they must differ by a unit phase factor. Okay? And this must happen for every state. So any representation of a symmetry must obey this relation. These kinds of representations are called projective representations. Are we on board with that, people? Any questions?
Maybe it's trivial what you're saying.
Okay. A subcategory of these kinds of representations are the unitary representations, where omega here, the phase factor, is equal to 1, irrespective of the elements G and G prime. Okay. In this case, the unitary this group is called the unitary representation. This omega factor cannot always be chosen to be unity, and this is connected to the topology of the group. But I think I should not go into that. But I think I should mention the physical implications of a non. Sorry, this should be 0, not 1. I'm sorry. If omega is non-zero and we have a purely projective representation, this allows to construct states. Some states. We call these super selection rules, which do not allow you to have a linear combination of states for different mass or spin, for example. And these are common in nuclear physics, so I would suspect you know about this. So let's come to another theorem, which is due to Stone, who proved it in the mid-30s, I think. So if the element G is close to the identity, then you can represent each element of this representation as the exponential of a linear combination of self-adjoint operators. Okay, this is what we these operators form a Lie algebra in the sense that their commutator, the commutator of these, is also a linear combination of these operators. Okay, this is how you you define physical observables. Does anyone understand what I just said? So if you say that you have constructed a unitary a projective representation, okay? The generators of these representations are operators such that this relation holds, okay? Okay, so these generators are self-adjoint because otherwise this thing wouldn't be a unitary operator, okay? So generators of symmetries are physical observables, okay? Okay, so this is a situation similar to a situation in classical mechanics where you have symmetries like translations, time and space translations, rotations, and boosts generated by physical observables. Sorry. We call the generator of time translations, in direct analogy with classical mechanics, the Hamiltonian. The momentum is defined as the generator of space translations. The angular momentum is the generator of rotations, and etc. Okay? Did I lose you there, people? Okay, let's move on. So let's consider an absolutely free particle, okay? Meaning that its symmetry group is the full Poincaré algebra of that generate the Poincaré group, okay? Now, if you do have this as an exercise so that you can understand it better, if you do the calculations, this thing is a multiple of the identity. Does anyone know what this is? This is actually very important, a very beautiful result. What is this? This is the mass. So if you have a quantum system, then its symmetries, the group of all symmetries, if you take its symmetry group and map it to its Hilbert space, then you get that the mass of the particle is an invariant. Mass follows simply from space-time translations, symmetries, sorry. Do you understand this?
Sorry, to be pedantic, shouldn't it be mass squared?
Yes, mass squared. This is the mass squared. But this is how you actually how you arrive at the mass of the particle. People, is this clear? This is very important.
I guess, yes.
Okay.
Yeah.
So let's go to the position operator. We haven't talked about position yet, right? So the position, the physical observable defining the position does not really come from the symmetry group. It can be defined not directly, but it can be defined by its properties. So the the first property is that it must be rotated as a vector. If you apply a rotation, then it should be rotated as a vector. I have written some exercise in which you actually go about proving this result. And if a set of operators is transformed as a vector, then you get these commutation relations. Okay. The second property is that it can be translated as a vector. If you apply a transformation generated by the momentum, then the vector formed by these operators is also translated as a vector if these commutation relations hold. All of these are exercises in the notes that I have prepared. Okay, so please do them and contact me if you have any problem. And there is no length contraction. We are talking here in purely Galilean spacetime. Okay. So if you have a free particle and an operator satisfying all of these relations, and you require furthermore that its velocity, which is defined using the Heisenberg picture, if your velocity is translated also as a vector, if you apply boosts, then you get the position operator. Is everyone clear on that? Does everyone understand this?
Where are you going, Costa? Can you back up? Can you make a summary?
Yes, sure. So in discussing the symmetry properties of a free particle, at no point did you have the concept of a position operator. There was no observable quantifying what a position operator is. Okay. So just by using the symmetry group, you didn't get a physical observable corresponding to the position, right? You only got generators of translations and rotations, right? So where is the position operator? The answer is that if it is defined indirectly by assuming that there is such an observable transformed as these properties show, then you get that the position must be given by this relation. Do you understand this now?
Mm-hmm.
Okay.
So, can I ask a question?
Of course.
So first, the trivial thing. You put h bar to 1 everywhere? Is that? Or...
This is for operators.
Okay. So you sort of define everything mathematically by absorbing the h bar or something like that?
Yeah.
Okay. So, yeah, I'm puzzled by the commutator of x with k.
Yes.
Because I would normally think of k as being a sort of rotation in space-time, so it involves the...
No, I mentioned earlier that we are talking about non-relativistic particles, so there is no length contraction. This is...
In the previous page, it looked relativistic.
Yes, I mentioned in the beginning that we are talking about Galilean particles because for the Galilean particles, it's actually simple to do that. In relativistic particles, actually, this is impossible. I think Wigner and a guy named Newton wrote a paper together showing that these kinds of definitions do not work for a position operator for relativistic particles.
Okay, excellent. Thank you.
And the second theorem is that you get spin. If you define spin as the difference between the generator the angular momentum, the total angular momentum, minus the orbital angular momentum, then you get spin, which is a parameter is not related to the position or the momentum of the particle. People, this is very important. Are you following me in this? Okay. So what I wanted to show is that based on purely on the concept of symmetry and essentially the principle of relativity, you can get very, very beautiful results regarding what is spin or mass. How do we go about defining these properties of a quantum system? Okay. This is actually very important, and I have this. I have written all of these results in the form of exercises. So if you don't understand it, you can read it later. Okay. So let's move on. If you're doing, if you have done. I assume that you have done many exercises in your undergraduate courses where you either worked in the momentum representation or the position representation. So the question is, how do you go from one to another? And the answer is given by Neumann's theorem, essentially, which states that no matter what your choice for the representation that you use, if you use the same spin, then all your results will be identical. Okay? Does anyone follow? Any questions? Okay. So all representations of the same spin and mass of a non-relativistic particle are equivalent, essentially. Okay, so you don't need to basically to worry about which representation you use, but there is a problem. This works only if the representation is finite. If you have an infinite, if you're trying to do this for an infinite number of particles, this fails. And this is a problem for quantum field theory. In quantum mechanics, the theorem by Stone and von Neumann usually is used to prove that no matter what your quantization is, you will always get the same results. But if you try to quantize a system with infinite degrees of freedom, then you may have a problem because two different quantizations might give you physically different results. Does everyone understand this? Okay, let's move on. Sorry, did I heard something? Okay, probably my idea. Okay, so this concludes the first part, which says that particles, the properties of particles are described using representations of symmetry groups to the state space of the quantum system under study. Okay, things like spin, mass, etc., are described via these generators. Okay, so let's go to quantum field theory, which is.
Can I interrupt and ask a question?
Of course.
So this is an extremely counterintuitive definition of a particle, right?
Yes.
You might almost advocate dropping the word particle because
exactly
there's nothing in your definition
exactly
that looks like a point.
Exactly.
So what do you think about that?
This is something I'm still trying to wrap my head around.
Okay, excellent.
I'm often so when I'm studying these things, I'm often reminded by a quote by I think it was by Born, who said that we should drop classical intuition about what a particle is and ask what are the parameters that can be observed. I think intuition kind of fails, and you should talk about what you can measure and what not so much as what should be measured, because it might lead to applying classical intuition to somewhere where that's impossible, right?
Right.
Okay. So let's move to quantum field theory. Weinberg wrote an article, I think it was during the 90s, in which, I might be mistaken, in which he claimed, and he does this in his textbooks, Quantum Theory of Fields, the first volume. Quantum field theory can be derived in a similar way using symmetry plus causality, and the postulates are the following. You start with a scattering theory. Let's go to relativistic particles, and you start from scattering theory. So if you have an S matrix in which you impose that the interactions come from a representation of the Poincaré algebra, essentially you assume that your system is characterized, the scattering is characterized by Lorentz covariance. And you have a causality condition known as the cluster decomposition principle. Has anyone heard of this? This is not usually done in quantum field.
Wait, sorry. What do you mean by scattering?
Scattering means that you start from particles that are from a system of particles, which are a system of particles which is asymptotically free in the past. Okay. You have a short range, essentially a short range interaction, and what you get is a different system of particles that is asymptotically free in the future. Okay.
Okay.
Yes.
Can I be pedantic?
Of course.
Thank you. Going back to Neil, because he asked, where is the intuition about a particle here? Because it is mathematical.
No, there is no.
Yes, but what is a notion of a particle in physics, right? A point-like object. But how can you define a dimensionless point thing?
I have a.
How can you bear weight, charge, mass? It's like, at least I don't know the answer. It's like, it's fundamental. You assume that it's a point-like thing, but I don't have any information about it.
I didn't make, I didn't make any assumption on the volume.
No, Costa, I'm not attacking you. I am
I'm explaining that position. So if you try to define a particle, saying it's a point particle, means that you can ascribe to it kind of position, right? It has size, but this is not well defined. You can localize it. But,
yes, you can say it's a collapsed waveform.
Yes, you can localize it, but fundamentally, in a fundamental level, you cannot easily ascribe to it a position, an observable, which we would call a position. There have been, for relativistic particles at least, there have been some attempts in constructing a position operator, but they are not equivalent with each other.
Yes.
And
So this is actually a question to Neil. So what is a particle for you? Is it a collapsed wave function? Is it a quantum excitation of a field? Is it a irreducible representation, I don't know, of a group? What is it?
So, yeah, so I think this is a very fundamental problem. And the trouble is that this problem is the beginning of problems with quantum gravity.
Yes.
Because the whole idea of quantum gravity is, it comes from trying to, you take a classical framework, which is a geometrical space-time, and then you try to quantize it. So if I do the same thing with a particle, I would take a classical particle in relativity, which has a beautiful geometrical definition. It's a world line in space-time. And then I would try to quantize that. And the fact that we cannot do it easily, well, we can do it in a certain sense. I mean, one has the uncertainty principle. So if you fix the position exactly, of course, the momentum is absolutely unknown. But still, this is exactly what experimentalists do, right? They measure and they find the photon hits the screen at a particular position. So the measurement is made and you know where the photon was at that time exactly. So I think there is a way to do it, but it's in, I completely agree, it's in tension with this definition through symmetries.
Yeah, but you understand I am playing the devil's advocate.
Yes. Yes. So this is the reason that I'm trying to do this presentation, is actually to show problems with very fundamental concepts and have people interrupt me and point out these problems.
Yes.
So thank you for the interruption, and if you could interrupt me more, I will.
Right. I mean, to me, it sounds like this definition is designed for S-matrix theory, where
not only that, it has problems which I will mention in 5 to 10 minutes.
Okay, so, great.
Yeah.
Costa, by the way, what is an S-matrix? I don't know anything.
Oh, you can. So the S-matrix, I think people who are doing nuclear physics are very familiar with it. An S-matrix is the you can think of it as the transition amplitude from a free incoming state to a free outgoing state. It's a purely, how should I say this, phenomenological tool. You're trying to measure the transition probability from a free state that you have prepared your system initially to an outgoing state after the experiment.
What do you call it, the S-matrix and not potato matrix?
Because it's formalism. I think it's just called S-matrix.
I think it's from scattering.
Yes. Yeah.
Yes. By the way, I have here some questions by Bikram because he has a problem with his microphone.
Sure.
So
okay.
I'm going to read them aloud. So first of all, what would happen if you consider time also to be an operator in quantum mechanics?
This is an excellent question. So there have been some theorems. I remember studying this in undergraduate quantum mechanics some years back. If you try to develop a time operator an operator for time, then you would get a violation of the second law of thermodynamics. Due to some, I'm not sure, maybe Neil can correct me, but if you assume that there is such an operator, then it must, then under the action of the Hamiltonian, it must be translated.
But aren't we violating thermodynamics in a way all the time?
Wait, I was getting there. So this gives you a commutation relation, which in turn shows you that, if I remember correctly, this shows you that the Hamiltonian is unbounded from below. So you could, in principle, construct a system which would decay indefinitely. It would not have a ground state, so it would decay and releasing energy, and it would.
So you would have a boundless, so an infinite amount of energy.
Yes, you would basically have a violation of the second law of thermodynamics.
But that's fine. We do that in, for instance, in stellar dynamics all the time, and we're fine with it.
Well, maybe the problem there is it's just that you're trying to apply thermodynamics to a system which does not have a thermodynamic limit.
Well, a self-gravitating system has no thermodynamical equilibrium. But anyway, I was just joking. He has a second question for you.
Yes.
He says, here you talk about different Lie groups like SO2, SLN.
These were examples so that the students could understand.
So but the question continues: are these Lie? So these are Lie groups? They also have the corresponding Lie algebra, but as we know, if we have a metric like in general relativity, then we can easily calculate the Lie algebra of that metric. So my question is, can we construct a similar metric for quantum systems also? How would it look like?
So the question is whether you can construct a metric from
a similar metric for quantum systems.
But you already have a metric. It's the inner product of the Hilbert space. Yes, so when you're talking about the Hilbert space, a Hilbert space is an inner product space, which is also complete as a metric space. So you already have an inner product.
Yes, okay? I agree with that, yes.
Okay, so are there any more questions?
Not on the chat, but
I
what
assume
about the rest of the participants? Solne, come on, Oris, Maligno, Diana, silence.
Okay.
Well.
I assume that they understand it and we'll move forward. So the second, coming back to constructing quantum field theory, I will not actually do it, but I can point you to the to Weinberg's book, Quantum Theory of Fields, Volume 1. The second postulate is the cluster decomposition principle, which states that experiments done in space-like disconnected regions yield uncorrelated results. Okay, and a third condition is rather technical. It's a localization condition, but let's keep it because it doesn't really give you an intuition. So the problem is that this thing, if you try to do this in a quantum, if you try to do this in a curved spacetime, now we come to something that I really do know. If you try to do this on a curved spacetime, this breaks down. And this is actually related to what Dafermos presented in his lecture. Can anyone think of why this construction scheme breaks down if you have a sufficiently curved space-time?
I know.
Not you.
Come, people, get a guess. It's not that you're getting a mark after this or a note.
Yes, I'm nowhere near qualified to mark you. Not a good physical reason. People, do you remember about the singularity theorems?
I don't. What is it?
So the singularity theorems basically tell you that if you have sufficiently enough dense distribution of energy and momentum, you get what we call a singularity. Singularity is happens when you cannot go, when there are histories with a finite past or future. So the problem is that you cannot have an S matrix if you do not have a finite, if you have a finite past or future for some states. Do you understand this? Scattering theory implies that the past, that you can go infinitely back to the past or to the future. So you have essentially a breakdown of scattering theory itself. Okay? Do you understand this? There are actually a lot. Yes? Did someone say that?
It's me again. I was trying
Can you
to... Pasu, yes?
No, I was just saying if you can repeat once more.
Repeat what?
The localization condition.
No, I said it was a technical condition on the interaction, and it's not really relevant.
Okay, all right.
This is
The
Sorry?
scattering and I think it's about the scattering and the need to the infinity part.
I didn't understand the question.
No, I think that Vasu wants you to repeat the part that if you have a finite that the scattering needs an infinity.
When you're trying to mathematically formulate a scattering experiment, you assume that you can go infinitely backwards in time and infinitely forward. Otherwise, you cannot construct a scattering. You cannot mathematically construct a scattering experiment. Does that answer your question?
Yes.
Okay. There are actually a lot more difficulties in actually constructing a curved spacetime. If I hope that you recall that all of our observables were constructed on the basis of symmetry. In a curved spacetime, you might not have a symmetry. You might have locally, but globally you might not have any kind of symmetry. So if you do not have a rotational symmetry or even a translation symmetry, how can you define the spin of a particle? How can you define these kinds of observables? This is actually a question from me to the audience.
But what kind of symmetries do you have? Like,
you may not have any kind of symmetry. In a dynamical space-time, like, for example, when you have two black holes rotating, what happens? You do not have an axial symmetry. You do not have a time symmetry. Not have rotational symmetry. You do not have any symmetry, right? So how can you construct things like spin? One solution could be that you appeal to the principle of equivalence, that you construct these things locally. But then you come up against another problem. There is no invariant ground state. If you try, so there is this phenomenon called the Unruh effect, where say that you have two observers, one is at rest and the other is accelerating. The observer at rest, we will see, if the observer at rest will see, for example, a quantum field at the ground state, the accelerating observer will actually see the ground state to be in thermal equilibrium with a thermal bath. So you do not have a ground state which is invariant with respect to diffeomorphisms, with general coordinate transformations. So you break general covariance, which is essential in relativity. This is actually something that I think we discussed this together, Neil, at some point. I think it was
Yes.
on People's talk. So the concept of a particle as an excitation of a field is kind of in question here. Because one observer, even in a flat Minkowski space, one observer sees no particle, the field is in a ground state, while the accelerating observer sees a thermal sees radiation.
A thermal bath.
Yes. So there are problems in our definition of a particle and in quantum field theory in general, when you try to introduce things like curved spacetime, which are intimately related to relativity, to the geometry.
But Costa, maybe you should explain here that in quantum field theory, the concept of vacuum is not equivalent to empty space, right?
No, I didn't mention anything about the vacuum. I said that the ground. I said that that one observer sees a ground state, and the other observer sees thermal radiation. I didn't say anything about vacuum.
No, but the Unruh effect is about implies the notion of vacuum, right? So that the notion of vacuum depends on the path.
So the Unruh effect, yes, but vacuum is another name for ground state.
Okay.
Vacuum. So in quantum field theory, we the names ground state and vacuum are interchangeable. Okay. So how do you resolve these problems? We have a lot of qualified professors here that can give a much better answer to this than me.
Who is a qualified professor?
Neil, for example. I can't see.
I don't have any answer.
By the way, Costa, what is the Unruh effect?
It's what I said earlier, that an accelerating observer, so that you have say that you have a simple quantum field, which is in ground state with respect to an inertial observer. an accelerating observer will not see ground, so it will instead see thermal radiation.
And how is that possible?
I don't know. I mean, it follows. What I mean is that it follows from the laws of quantum field theory and relativity, but I can't say that I understand this result at a deep level.
And has this been observed experimentally?
From what I think not.
What about this Sokolov turn-off thing?
Sorry?
There was this Sokolov in Russian. So I don't know how to say it in English.
I don't know. I haven't heard about these experiments, but something that I would like to mention is that the Unruh effect is often used to prove that black holes radiate. So this is not something that should be taken lightly, and I think it's very important to understand these problems for future research.
Costa, is different. Conceptually, is different. The Unruh effect than the Hawking radiation.
I know. That's what I said. I said that it's often used to prove, theoretically, of course, that black holes radiate.
Yeah. No, it's not the same calculation. It's a different one. It looks like the same, but it's not the same. Actually, there is a very conceptual difference here, which is the presence of the horizon in the case of black holes. I think that...
Sorry, go ahead.
No, I just wanted to mention that all these problems that you are mentioning, I think that what people have been trying to do is that it's not that there is a quantum field theory for everybody in the space-time, right? I agree that it's very difficult to, without having symmetries and, I mean, handles that you can use to define things like, as you said, like energy or things like this. It's difficult. But one of the things that people has been doing, and I'm not saying that is successful. Actually, I think that this is where you have the breaking of quantum field theory in curved space-time, and is that in the end, it's like there is a quantum field theory for each observer. So for you can have observers, like, I mean, fiducial, if you have a black hole, you can have a fiducial observer that is somebody standing outside the black hole, and then you can do many calculations in quantum field theory, and things look okay. The problem is that when you now do the same calculations from, instead of a fiducial, let's say, standing observer outside the horizon, you want to do the same for a free-falling observer, and then you see things that are completely different. And but I think here we are going to follow a line of discussion and argument that has not yet been ended in the physics community already. That is what my vision of this.
Yes, that's what I mentioned, is that if you try to, you cannot have a general, from what it seems, that it's not possible to construct at the moment a generally covariant quantum field theory. I think Neil wanted to interrupt.
But don't. I think that I don't think general covariance is the same thing as having different observers. I think it's, at least in the case of quantum theory, is something that is different, conceptually different. Because, I mean, general covariance in the end means that your equations are invariant under general coordinate transformations, which probably is true. Yeah, so this is not the problem. The problem is what happens when you change from one observer to other and try to do physical predictions from these observers, trying to build a sort of quantum field theory in the space-time.
I think Neil wanted to interrupt me even further.
No, I just wanted to say the Unruh effect also involves horizons, because an accelerated observer cannot see the whole of Minkowski space.
Yes. But it's
So,
a particle horizon, right?
yeah,
The
it does.
window horizon.
And so there are similar features to the black
Yes.
hole. But no, I think the notion is, and it's a very shocking notion, that it's what you said, that the quantum field theory, the vacuum is observer dependent.
Yes.
So somehow the whole idea of a vacuum in the quantum field theory is observer dependent. And it relates a little bit to what you were saying about that, the energy being unbounded below, if you really insist on time being an operator. That you're trying to build, in general relativity, there's no difference between time and space, really. I mean, there's a minus sign here and there, but conceptually they're very, very similar. And then when you come to quantum field theory, you really can't have both as observables. Otherwise, you have the Hamiltonian being unbounded below.
Yes.
Now, the quantum field theorists may conclude, okay, we can't apply these notions in quantum field theory. I think somebody less, who's more enthusiastic about general relativity would have to say, well, quantum field theory is very limited then. And somehow these issues must be resolved in general relativity through some other way. And I think that's probably true. I mean, quantum field theory, as I mentioned in my talks, is really built on the Wick rotation, where time becomes space.
Yes.
And Weinberg does not explicitly say that in his book, but that's because he's always doing perturbation theory.
Exactly. This is what I was actually coming to.
Okay, good. Okay.
So I wanted to say that until now I have sort of presented the argument symmetry versus quantization, canonical quantization. I haven't mentioned path integrals because because I have we have an expert on this in the panel. So and the problem is that as Neil has presented, we have not spent much thought in the path integral in order to quantize a system properly via path integrals.
Yeah, it's difficult.
Yes, and since Neil has already done a presentation on building from a path integral, actually explaining the problems of a path integral, I wanted to mention an article by I think his name is Kao or Chao. I'm not really sure. Carol and Michalakis, another Greek. We Greeks are like cockroaches. We seem to prop up everywhere.
No, there are not so many. The first one is Chen. It's Cao.
Okay. So
I'm not this Michalakis. That's all I want.
Yes, he has done wonderful work in quantum, in mathematical quantum physics.
But by the way, if I may, don't call the first guy never ever in your life a Tao, because that means something completely awful, and you should avoid that.
Why? Okay, you can explain to me later. But anyway, what I wanted to mention here is just give some kind of an FYI that there are theories beyond simply quantization. And this effort actually discusses how you can get an emergent space just from Hilbert space.
Mm-hmm.
So in essence, what you can think of two systems. I'm going to explain this very crudely so that people in the audience can understand what they distance according to this this model that they've developed. Two systems are close to each other if they are entangled strongly, and they are far from each other if they are entangled weakly. So you get some kind of a geometry in which closeness is identified with the strong entanglement. And they actually derive a relation between the energy and the entanglement. Yes. I hear some. Does anyone want to ask something? Okay. So they identify closeness with entanglement, and it's something that is very elementary in terms of its requirements. You only require a Hilbert space, essentially. And I think people should take a look at this. So it's something of a third-party outreach talk. Anyway, this is the material I wanted to present. If anyone has any questions.
So this diagram is so crude.
Sorry?
This plot is so crude.
Why is it crude?
No, I'm just trying to make a joke because you said it was very crude.
You kind of failed, but anyway.
So, what is... do you have questions for Kostas? So, have you followed?
By the way, I should mention this again. I have prepared some exercises for the student to fill in the gaps in today's presentation. I hope you will take a look at them. And you can, of course, contact me if you have any questions, of course.
May I ask a question?
Of course.
So I just wonder if you can, the spirit of this proposal of space from Hilbert space,
yes.
Presumably, I mean, I'm wondering, why is it not space-time from Hilbert space? And is it really true that diffeomorphism invariance is supposed to come out of entanglement?
No, I didn't mention anything about diffeomorphisms.
Right. So can you, what's the basis for this hope that geometry will emerge from Hilbert space? What's the basis for it?
A basis in what sense? Can you elaborate on that a little bit?
Is there any evidence that?
Of course not. There is no evidence. What they did is that they present a compelling direction. This is why I wanted to mention it.
Right. What's compelling? Tell us why you find it compelling.
I find it very compelling because it requires, it doesn't really require much in constructing space. You just start from a Hamiltonian and a Hilbert space.
Is there a simple example where, some collection of Hamiltonians and Hilbert spaces gives rise to something like a geometry?
I think they did it in their paper, but I'm not really sure I understand it completely because it was getting a little bit technical,
right.
And I haven't encountered this before.
Okay, thank you.
But a lot of people who have not asked anything. I mean, Kostas, and he doesn't bite, and he's very nice, etc. Any kind of question would be more than fine.
I don't bite much. Tend to bite sometimes.
Nikos, you didn't say anything.
What am I supposed to say?
But you don't know. You can complain.
That's encouraging.
You can say that you don't like that drawing, that it sucks. I don't know.
No, really, it was from all I could watch. It was nice. There's nothing that I was worried and was not already mentioned. So,
okay. Well, I don't know.
Just one thing.
Yes.
If I'm not wrong, and Neil might remember that better, it was Dirac who first said that there's a fundamental problem in quantum mechanics and the fact that you cannot quantize the world lines of a particle. So that's something that quantum physicists should go back and check.
That you cannot quantize the word lines?
Yeah.
Or that you cannot quantize?
You cannot. You cannot.
I think it was Bohr, but I might not be 100%. I'm not 100% sure.
Yeah, I thought it was Dirac, but anyway, it was quite early in the development, and I think it is still pretty much unresolved. That's very interesting that it's quite unresolved.
Any questions?
Well, if not, remember that Kostas has actually put a lot of time into preparing that list of exercises, which I have seen, and it really pays off to look at them and try to resolve them. Joel, you can just talk. You don't have to raise your hand.
Yes, maybe. I don't know if this is a good question, but can I say that from the talks that quantum mechanics has a problem? For example, in this last picture you showed and everything before trying to describe particles through properties, that there is a problem between trying to create the algebra that we commonly use through quantum mechanics.
Yes.
Is that a good conclusion?
I mean, the fact that we cannot construct this algebra is hinting that it's what I said at the last minutes of my talk is that we cannot define quantities, measurable quantities like a spin or the very definition of the particle in the same way that we can in usual quantum mechanics, and I think that's a problem that should be addressed.
Okay, but for example, point particles come from classical physics.
Yes.
And in this last picture you show, I think that if it works, it might describe a point particle through space description.
I haven't mentioned anything about a point particle.
Yes, I know. What I mean is that during the talk you said that particles were described in quantum mechanics through their properties.
Yes, through yes.
Okay, so in this when I think about a point particle, I think that one of the main things to develop is the geometry, the space geometry, right? How we describe the form of this particle.
So if you have this method that I presented about describing a particle in terms of angular momentum, mass, etc., relies on the presence of symmetry which may not exist in curved spacetime, and that's a problem when you have curved spacetime. That's what I said.
Okay. Thank you. Yeah.
Sure, no problem. Any other questions? I mean, I shouldn't take Carlos's time because I will feel extremely bad.
No.
Okay. Well.
If you have any other questions, you can always reach me by email. I think Pau will upload it on his workshop page. I will be more than happy to answer questions and help you with the exercise if you need.
Send me the slides and the exercises I have. No, you did already both. Okay. So people, let's come back at 40. Okay.
Okay.